Suzuki cars are built with precision and engineering that pushes every component to perfection. Inside the factory, raw materials are transformed into sleek, road-ready vehicles through a combination of advanced robotics and skilled craftsmanship. Today, we're stepping onto the production floor to see exactly how a Suzuki goes from blueprint to the open road. The journey starts as a concept long before steel meets the press or engines meet the chassis. Engineers and designers spend months, sometimes years, refining the blueprint of a model. Every curve of the bodywork, every mechanical component, and every safety feature is planned with meticulous care. It is not simply about designing something that looks appealing, but ensuring that every component can be manufactured reliably, assembled efficiently, and maintained for years of use. When the design is finalized, the preparation for production shifts into the realm of manufacturing engineering. This is where the physical requirements for building the car are translated into a sequence of processes, machines, and assembly operations. The factory layout is adjusted to accommodate new tooling and equipment. The stamping presses, welding robots, painting lines, and assembly stations are prepared in harmony, ensuring that the entire flow of production can move like a well-orchestrated symphony. Each department communicates with the others to align their timing, capacity, and technical requirements, because any mismatch between stages can create bottlenecks that slow the entire plant. Before we even see the first car body taking shape, we must understand the raw materials that feed this system. The backbone of every Suzuki vehicle is steel, but not just any steel. High-strength automotive steel sheets arrive from steel mills in giant coils, sometimes weighing over 20 tons each. These coils are delivered by rail or truck to the factory's stamping plant. Alongside steel, aluminum panels, plastics, resins, and a variety of other materials are delivered in a steady flow. The supply chain for a car factory is an ongoing pulse of incoming goods, timed precisely so that inventory storage is minimized. Many parts and sub-assemblies come from a network of suppliers that specialize in producing components such as seats, dashboards, headlights, and braking systems. Some of these suppliers operate right next door to the Suzuki plant in what is known as a supplier park to enable just-in-time delivery directly to the assembly line. The steel coils, once unloaded, are stored for only a short period before being moved to the stamping department. This is the first truly transformative stage of car manufacturing. In a cavernous hall filled with the rhythmic thunder of stamping presses, the steel sheets are uncoiled, flattened, and fed into enormous press machines. These presses exert thousands of tons of force, shaping the steel into the contours of fenders, doors, hoods, and roof panels. Each press operation uses dies, massive, precisely machined blocks of steel that mold the sheet metal into exact shapes. The dies can weigh several tons and are swapped out when changing to a different panel design. A single car body panel often requires several stages of pressing, beginning with a rough form in the first die, followed by progressively more refined shapes in subsequent dies, until the panel meets its exact specifications. During stamping, every millimeter matters. Automated optical inspection systems check the freshly pressed panels for surface defects, ripples, or dimensional deviations. Any panel that does not meet standards is set aside for recycling, its metal returned to the melting process to be reformed into new sheets. This reduces waste and ensures that only flawless panels proceed to the next stage. The next stop for these panels is the body shop, an enormous section of the plant where the raw pressed steel pieces come together to form the recognizable skeleton of a Suzuki car. Here, the air is filled with the bright sparks of robotic welding arms. The panels are loaded into large jigs and fixtures that hold them in precise alignment while robots perform spot welds. These welds fuse the panels together permanently, ensuring structural rigidity and safety. For a modern Suzuki, this stage is heavily automated, with banks of robots working in perfect synchrony. However, skilled human operators remain essential for overseeing the process, making adjustments, and performing welds in tight or complex areas where robots cannot easily reach. The construction of the car body, known as the body in white, follows a carefully choreographed sequence. The floor pan, which forms the base of the vehicle, is placed first. Side panels and door frames are aligned and welded onto it, followed by the roof, front, and rear sections. Cross members, reinforcements, and brackets are added in specific places to enhance crash protection and structural strength. Door openings are checked against strict dimensional tolerances to ensure that later, when doors are hung and adjusted, they will fit perfectly without rattling or misalignment. At various points in this body shop process, quality control engineers measure critical points on the structure using laser scanners and coordinate measuring machines. This prevents small errors from compounding into serious alignment issues later. The body in white, once fully welded, is a bare shell of gleaming steel. It has no paint, no trim, no glass, but its proportions and integrity are set for the rest of its life. Before painting, the bare metal body must be prepared meticulously. Even tiny traces of oil from stamping or dust from welding can cause paint defects. Therefore, the bodies are sent through a cleaning and pre-treatment line. They are dipped in a series of chemical baths that remove contaminants, apply a phosphate coating to improve corrosion resistance, and prepare the surface for paint adhesion. This pre-treatment line is fully enclosed, and the bodies are moved on an overhead conveyor through each tank, sometimes fully submerged, to ensure every crevice is treated. The final step in this stage is a drying oven that removes all moisture. Only then does the car proceed to the paint shop, a section of the factory that feels completely different from the noisy stamping or welding halls. Here, the environment is controlled for temperature, humidity, and cleanliness. Dust particles are the enemy of smooth automotive finishes, so the entire paint area operates with filtered air and positive pressure to keep contaminants out. The first layer to be applied is the electrophoretic primer, also called E-coat. The car body is immersed in a bath where an electric current causes primer particles to bond evenly to every surface, inside and out, including hard-to-reach cavities. Once the primer is cured in an oven, sanding robots and human operators smooth the surface before the application of the base coat, which provides the car's color. Depending on the model, Suzuki may use robotic spray arms that follow precise patterns to ensure even coverage, especially around edges and curves. After the base coat, a clear coat is applied to provide gloss and protect the color from ultraviolet damage and environmental wear. Each coat is baked at controlled temperatures to ensure hardness and adhesion. As the painted shells emerge from the curing ovens, they are inspected under powerful lighting in what is often called the light tunnel. This is a controlled environment where every curve of the car's surface is scrutinized by trained eyes and optical sensors for even the smallest imperfection. A speck of dust caught under clear coat, a ripple in the finish, or an uneven tone in the paint can be enough for a vehicle to be sent back for refinishing. In automotive manufacturing, these cosmetic checks are not mere vanity. They are essential to meeting customer expectations and protecting the long-term integrity of the finish. Only after passing these surface quality tests does the body proceed to what is known as the trim line. The trim line is the first phase where the car begins to be filled with the parts that make it functional and comfortable for passengers. The process is meticulously sequenced. Every car moving down the line has a build specification loaded into the plant's production system. This ensures that the correct color interior, optional features, wiring configurations, and mechanical components are installed at exactly the right point. Workers and automated equipment access the build information via monitors or handheld devices, so there is no guesswork about which parts to install. The first installations are typically sound deadening materials. large sheets of insulating mat are fitted to the floor, inside the doors, and sometimes behind interior panels to reduce road and engine noise. Wiring harnesses are then routed through the body. These harnesses are pre-assembled bundles of wires that carry electrical signals to lights, sensors, power windows, and entertainment systems. Fitting them correctly is critical. Any pinched wire or poor connection can lead to costly troubleshooting later. Harnesses are secured with clips and ties to prevent movement or abrasion over years of use. While the wiring is being routed, HVAC ductwork is fitted, ensuring that heating and cooling air can reach every vent in the cabin. This is followed by the dashboard assembly, which is often delivered as a complete unit from a supplier. Installing a dashboard is a delicate maneuver, as it must align perfectly with mounting points while accommodating wiring connectors, instrument clusters, and control modules. A team of technicians guides it into place and secures it with fasteners that have specific torque requirements to avoid rattles or stress on the materials. Seats are another major interior installation. These arrive pre-assembled, complete with upholstery, cushioning, and any built-in electronics such as seat heaters or airbag modules. Using mechanical assists to avoid strain, workers position the seats in the cabin and bolt them to the floor mounts. Seat positioning is not only about comfort, it has to align with seatbelt anchor points and airbag deployment geometry for safety. Parallel to interior fitting, work begins on marrying the body to the mechanical heart of the car, the chassis, and drivetrain. This is a carefully timed coordination between two moving lines, one carrying the prepared body shells and another carrying the assembled underbody module, which includes the engine, transmission, suspension, exhaust system, and braking components. The underbody is prepared in a separate section of the plant, often referred to as the chassis line, where technicians and robots assemble the engine and transmission onto a subframe, attach the front and rear suspension assemblies, mount the exhaust system, and connect steering linkages. In the case of Suzuki's smaller passenger vehicles, these assemblies are designed to be compact yet easy to service, with many components integrated into modular subframes. This not only speeds up initial assembly, but also allows for easier maintenance during the vehicle's lifetime. The wheels and tires are sometimes fitted at this stage, though final torque on wheel nuts may be left until later in the process to account for transport considerations within the factory. The moment known as the marriage is one of the most striking in car assembly. The painted body shell is lifted slightly above the moving chassis assembly by a synchronized hoist system. As the chassis slides into position beneath the body, the two are lowered together, and a team quickly secures them with precision fasteners. At this point, the car's major structural integration is complete. The engine and drivetrain are physically connected to the body. Once married, the vehicle moves to stations where cooling lines, fuel lines, and electrical connections between the body and chassis are linked. This requires careful attention to routing, sealing, and securing. Every hose clamp, connector, and grommet is placed to avoid chafing or leaks, as even a small oversight here could lead to operational failures after delivery. The next focus is glazing, the installation of windows and windshields. Modern automotive glass is bonded to the body using high-strength urethane adhesives, which not only hold the glass in place, but also contribute to the vehicle's structural rigidity and crash performance. Before installation, the glass edges are treated for adhesion, and the body's window frames are cleaned and primed. Robotic applicators or skilled technicians lay a precise bead of adhesive, and the glass is positioned using vacuum lifters to avoid direct handling. Proper curing of this adhesive is critical, and vehicles are timed through the assembly process so that the bond sets before the car experiences any structural flex. After the glass is fitted, exterior trim pieces are added. These can include weather strips, side moldings, roof rails, and badging. The fit and finish of these components are critical to the car's perceived quality. Misaligned trim can create wind noise or water ingress, while inconsistent badging undermines visual symmetry. The doors, which may have been removed earlier for easier access during interior work, are now reattached. They are hung on hinges that allow for fine adjustment, ensuring consistent panel gaps and smooth operation. Once aligned, the doors receive their inner panels, window regulators, locks, and wiring for power accessories. The tailgate or trunk lid undergoes a similar process, with alignment checked to within millimeter tolerances. As the car progresses down the line, more systems come online. Fluids are filled: engine oil, transmission fluid, coolant, brake fluid, power steering fluid, and windshield washer solution. In many plants, these filling systems are automated to ensure precise volumes and to reduce spillage. The first electrical power-up occurs at this stage, allowing the vehicle's onboard computer systems to initialize. This is the moment where workers can begin testing electrical functions like lighting, wipers, and infotainment displays. Once the newly assembled Suzuki approaches the end of the main assembly conveyor, the atmosphere in the plant shifts from a building process to one of verification and fine-tuning. This is the beginning of the commissioning stage, where the focus moves from installing components to ensuring that everything functions exactly as intended. The car is no longer just a collection of parts. It is a complete vehicle that must now prove itself ready for the road. The first stop after major assembly is often the wheel alignment station. Here, the vehicle is placed on a set of precision plates and laser-guided measurement systems that check the angle of each wheel relative to the chassis and to one another. Proper alignment is critical for handling stability, tire wear, and driver safety. Adjustments are made using specialized tools that tweak the suspension's camber, caster, and toe settings until the readings fall within strict tolerances defined by Suzuki's engineering specifications. This step also ensures that the steering wheel will be centered when the car is driven in a straight line, preventing an issue that would be instantly noticed by a new owner. Following alignment, the car moves to the fluid check and topping station. Although fluids have already been added during earlier stages, they are now checked for correct levels and quality. Any air bubbles in hydraulic systems, such as the brakes or clutch, are purged through a process known as bleeding, ensuring consistent performance. Coolant systems are pressure tested to confirm there are no leaks, and the fuel system is primed and checked for tightness to avoid vapor or liquid escapes. Each of these checks is both a safety measure and a warranty safeguard, as fluid leaks can lead to early vehicle failures. Now comes one of the most anticipated moments in the factory: the first engine start. At a dedicated station, the technician inserts the ignition key or engages the start button, bringing the Suzuki's engine to life for the first time. This is not a ceremonial step, but a critical diagnostic event. As the engine runs, technicians listen for abnormal sounds, check for warning lights on the instrument cluster, and monitor the readouts from diagnostic equipment connected to the vehicle's onboard computer. The engine control unit records any fault codes during the first start, and these must be addressed immediately before the car can progress. This step also ensures that fuel delivery, ignition timing, idle control, and emission systems are functioning properly from the outset. Once the initial engine check is complete, the car enters what is called the rolling road test. This is essentially a dynamometer station built into the assembly line. The vehicle is driven onto large rollers, which allow the wheels to spin as though the car were traveling down an actual road. The technician operates the vehicle through various speeds and loads, while sensors measure engine output, drivetrain smoothness, and braking performance. Onboard equipment also checks that gear shifts are smooth in both manual and automatic transmissions, that traction control engages correctly, and that the ABS activates as designed during simulated stops. For hybrid or electric Suzuki models, the rolling road test verifies battery performance and regenerative braking operation as well. After this dynamic evaluation, the car undergoes an emissions test. The exhaust gases are captured in a sealed system connected to high-precision analyzers that measure the concentration of pollutants such as carbon monoxide, hydrocarbons, and nitrogen oxides. The results must comply with the regulations of the market where the vehicle will be sold. If any parameter is out of range, adjustments to the engine management software or mechanical repairs are made immediately. Emissions compliance is one of the most heavily regulated aspects of vehicle production, and no car can leave the factory without passing this check. With the mechanical and electronic systems validated, attention turns to the finishing area. This is where skilled technicians examine the entire vehicle for fit and finish issues. The car is inspected under bright lighting and from multiple angles to detect paint blemishes, uneven panel gaps, or imperfections in trim alignment. Special gauges are sometimes used to measure panel gaps to within fractions of a millimeter, ensuring consistency from one vehicle to the next. In addition to visual checks, technicians test all customer-facing features. Every switch, button, knob, and lever is operated to confirm proper function. Windows are raised and lowered, mirrors adjusted, wipers cycled, and climate control systems run through heating and cooling modes. Infotainment systems are powered up to verify screen clarity, touch sensitivity, and speaker output. Even less obvious features, like seat height adjusters and child safety locks, are tested to avoid customer dissatisfaction. The underbody of the car is also inspected at this stage, typically with the vehicle lifted on a hoist. Inspectors look for fluid leaks, loose fasteners, or improperly routed cables and hoses. Protective coatings applied to resist corrosion are checked for completeness, especially around weld seams and in wheel wells where road spray is most intense. Once all systems are confirmed, the car enters the water test booth. This is an enclosed chamber equipped with high-pressure spray nozzles that douse the vehicle from every direction for several minutes, simulating heavy rainfall and splash conditions. After the soaking, technicians climb inside to check for any water ingress around doors, windows, or the trunk area. Sealing defects are corrected immediately, as water intrusion can lead to electrical failures and interior damage over time. If the car passes all these stages, it proceeds to the final audit line. This is often staffed by some of the most experienced personnel in the factory, as they perform a comprehensive review of the vehicle. The final audit is essentially a condensed version of all earlier checks combined into a single process. It includes visual inspection, functional testing, and a short, low-speed road test within the plant grounds. Any fault, no matter how minor, is documented and corrected before the car can be released. Once signed off, the vehicle's identification and tracking information in the production database are updated to reflect that it has cleared manufacturing. Protective coverings are then applied to vulnerable areas like the hood, roof, and interior surfaces to prevent damage during transport. From here, the Suzuki moves into the dispatch yard where cars are grouped according to their destination markets. Some are loaded onto specialized car transport trucks, while others are driven onto railway wagons designed for vehicle shipment. For export markets, vehicles are often taken to a port facility where they are driven into large car carriers, ocean-going ships with multiple decks capable of holding thousands of cars. Throughout this entire process, Suzuki's production philosophy emphasizes continuous improvement. Every issue found during assembly or final inspection is logged in a central system, allowing engineering and quality teams to analyze trends and implement corrective measures. This feedback loop ensures that problems are addressed at their source rather than repeatedly corrected downstream. Once a Suzuki car has passed its final factory inspection, and been fitted with protective coverings, its story shifts from manufacturing to logistics. This is a crucial and often underappreciated stage because even the most perfectly built vehicle must arrive at its final destination without damage, delay, or compliance issues. The dispatch yard of a Suzuki plant operates with the same precision as the assembly line itself, ensuring that each vehicle is correctly identified, grouped, and routed toward the market it is intended for. Vehicles are scanned into a tracking system using their vehicle identification number, or VIN, which serves as a unique fingerprint for each car. The VIN is tied to the car's exact configuration, model, trim level, color, engine type, and any special market-specific features. This tracking system communicates directly with Suzuki's global distribution network, allowing logistics planners to match production output to regional demand forecasts. The cars are arranged in neat rows within the yard, typically grouped by destination, so that loading can be performed efficiently. For domestic markets, the vehicles are usually transported by specialized car carrier trucks. These trucks are designed with hydraulic ramps that can be adjusted to accommodate multiple rows of vehicles, often up to 8 or 9 depending on size. Drivers are trained in securing the cars with wheel straps or chocks to prevent movement during transit. The loading sequence is carefully planned so that the first vehicles to be delivered are loaded last, minimizing handling at intermediate stops. For longer distances within the same country, rail transport is sometimes preferred. Trains can carry hundreds of vehicles in enclosed rail cars, protecting them from weather and debris. The loading process involves carefully driving each Suzuki up narrow ramps and into the railcar bays, with only centimeters of clearance on each side. Drivers in this operation are trained to maintain extremely slow, steady movement to avoid any accidental scrapes. The railcars are then sealed until they reach the unloading terminal, often located near major distribution centers. When cars are destined for international markets, the process becomes more complex. Export-bound Suzukis are loaded onto massive ocean-going vessels known as roll-on/roll-off ships, or RO-ROS. These ships function like floating parking garages, with multiple decks connected by internal ramps. Vehicles are driven aboard under their own power and parked in tight formation, with only enough space for mirrors and doors to avoid contact. Crews secure each car with wheel chocks and lashings to keep them stable during the voyage. Depending on the route, these ships can carry thousands of vehicles at once, stopping at several ports before reaching their final destinations. The voyage can last anywhere from a few days to several weeks, depending on the distance between the plant and the destination port. During this time, the vehicles remain sealed and untouched with their protective films and coverings intact. Because environmental conditions at sea can vary, including salt-laden air, the factory-applied coatings and transport wraps are specifically chosen to prevent corrosion or cosmetic damage. Once the ship reaches its destination port, a highly coordinated unloading operation begins. Teams of trained port drivers board the ship and drive the cars off in a continuous flow, following a pre-planned sequence. The cars are then parked in secure port storage yards, where customs clearance procedures are initiated. Every country has its own import regulations, and Suzuki's logistics team ensures that each vehicle's documentation, including emission certificates, safety compliance paperwork, and shipping manifests, is complete and accurate before customs inspection. After clearing customs, the vehicles are typically sent to a regional distribution center. Here, a process called pre-delivery inspection, or PDI, takes place. Although the car has already been tested extensively at the factory, the PDI ensures that nothing has changed during transport. Trained technicians remove protective coverings, inspect the bodywork for any transit-related damage, check all fluid levels, and verify that the battery is fully charged. tyres are inspected for correct pressure, and software updates may be installed if newer calibration files have been released since the car left the factory. This is also where market-specific adjustments are made. For example, vehicles shipped to countries with different lighting regulations might have headlight aim adjusted or daytime running lights enabled or disabled according to local laws. Navigation systems are loaded with the correct regional maps, and owner's manuals in the appropriate language are placed in the glove compartment. If a dealer has ordered optional accessories such as roof racks, spoilers, or upgraded infotainment units, these may be installed at the distribution center to avoid slowing down the main assembly line. Once PDI is complete, the cars are released for final transport to dealerships. Depending on geography, this may involve another short truck journey or additional rail transit. Dealers receive advance notice of incoming stock through Suzuki's dealer management system, allowing them to prepare showroom space and schedule customer handovers for pre-sold vehicles. When the cars arrive at the dealership, the process takes on a more personal dimension. Dealership staff conduct their own incoming inspection to confirm that the car is in perfect condition. Any final detailing, such as washing, waxing, or vacuuming, is performed to ensure a showroom-ready presentation. Paper floor mats, seat covers, and steering wheel protectors are removed, revealing the untouched interior. If the vehicle is destined for immediate delivery to a customer, the dealership staff will carry out the handover procedure. This involves explaining the car's features, demonstrating controls, and answering any questions the customer might have about operation or maintenance. The VIN is registered in the dealership system along with the customer's details, marking the official start of the warranty period. From the customer's perspective, the journey begins the moment they take the keys. From the factory's perspective, however, the cycle never truly ends. Feedback from dealerships about customer experiences, warranty claims, and any recurring issues flows back to Suzuki's engineering and manufacturing teams. This closed-loop communication helps identify opportunities for product improvements, process refinements, and supplier quality enhancements. Interestingly, the logistics chain is also part of Suzuki's environmental strategy. Modern vehicle transport planning aims to minimize unnecessary mileage and fuel use, sometimes even consolidating shipments from multiple manufacturers onto the same vessel or rail line to reduce emissions. In some markets, Suzuki works with dealerships to arrange bulk deliveries that reduce the number of trips and associated carbon footprint. In global terms, the distribution network is as critical to Suzuki's reputation as the production line itself. A flawless manufacturing process can be undermined by mishandled shipping, customs delays, or damage in transit. This is why Suzuki invests heavily in both technology and training to ensure that from the moment a vehicle leaves the assembly line until it arrives in the customer's driveway, it remains in the same pristine condition it was in at the final factory inspection. While the sight of finished Suzuki vehicles streaming out of the plant toward dealers and customers is the most visible sign of success, the real heartbeat of the company's manufacturing prowess lies in what happens behind the scenes. The precision of assembly, the timing of parts deliveries, and the consistency of quality all trace back to an intricate web of engineering coordination, supply chain management, and production system design. This interconnected system is what allows Suzuki to produce vehicles in large volumes without sacrificing the meticulous detail that defines a well-made car. The cycle begins long before the first sheet of steel is pressed, with engineering teams designing every component to be not only functional but manufacturable. This is known as design for manufacturability, or DFM. The aim is to ensure that parts can be produced consistently, at the right tolerances, and installed efficiently on the assembly line. For instance, a bracket might be designed with built-in alignment features that allow it to snap into place in only one orientation, eliminating the possibility of incorrect installation. Even the routing of a wiring harness is planned to minimize the number of bends and attachment points, reducing both assembly time and the risk of damage. This level of planning requires intense collaboration between product design engineers, manufacturing engineers, and even supplier representatives. Suppliers are involved early in the process to provide feedback on material selection, forming methods, and cost implications. A headlight supplier, for example, might work directly with Suzuki's styling team to adapt a design so that it can be assembled with fewer screws or clips, speeding up installation on the trim line. These interactions happen months, often years, before a model reaches production. Once the design is frozen, Suzuki's manufacturing engineers turn their attention to the factory itself. Every model introduction requires a detailed assessment of the production line layout, tooling, and automation requirements. This might involve installing new welding jigs for body panels, programming robots for different spray patterns in the paint shop, or creating custom assembly fixtures for unique components. Retooling a line is a massive undertaking, often done during scheduled downtime, to avoid disrupting ongoing production of existing models. One of the most critical decisions at this stage is determining the level of automation versus manual labor for each process. Suzuki, like many automakers, uses robots extensively for operations that demand absolute consistency, such as spot welding, seam sealing, and paint application. Robots excel at repetitive, high-precision tasks, and their ability to work in hazardous environments, like the fumes of a paint booth, improves worker safety. However, there are many tasks where human skill remains unmatched. Complex interior installations, final fit adjustments, and quality inspections often rely on trained technicians whose judgment and dexterity can adapt to small variations. For example, adjusting a door to achieve a perfect gap relative to the body involves subtle manipulation that a robot cannot yet match with the same flexibility. Suzuki's philosophy tends to blend automation with human oversight, creating hybrid workstations where robots perform the heavy lifting and humans ensure the final finesse. To keep everything running smoothly, Suzuki employs just-in-time manufacturing principles. This means parts arrive at the assembly line precisely when needed, rather than being stockpiled in large quantities. The benefit is reduced inventory costs and the ability to respond quickly to changes in demand. But this also requires a flawless supply chain, where every supplier delivers exactly on schedule. Any delay, whether from a parts plant, a transportation breakdown, or a customs holdup, can halt the entire assembly line within hours. To mitigate this, Suzuki maintains contingency plans and sometimes dual sources critical components so that production is less vulnerable to disruptions. The flow of materials within the factory is another area of intense engineering attention. Components are often delivered in sequenced racks, arranged in the exact order they will be installed. This eliminates the need for workers to search for the correct part, shaving seconds off each installation and reducing the risk of mistakes. In high-volume areas like the trim line, these seconds add up to major efficiency gains over the course of a day. Information flow is just as important as material flow. The entire production line is governed by a manufacturing execution system that tracks each vehicle in real time. As a body shell enters the assembly line, its VIN is scanned and its build sheet is instantly displayed. Suggest improvements, no matter how small. A simple change in the shape of a parts bin or the angle of a work platform can reduce strain, prevent errors, or shave time from a process. These changes are documented, evaluated, and, if effective, standardized across the production line. Quality control is embedded at every stage, not just at the end. Inline inspection stations use laser scanners, vision systems, and torque sensors to verify that parts are installed correctly and that critical dimensions are within tolerance. If a defect is found, the car can be diverted to an offline repair bay for immediate correction. This prevents issues from traveling further down the line where they would be more difficult and costly to fix. Equally important is the feedback loop between manufacturing and product engineering. When recurring assembly difficulties or component defects are identified, this information is relayed back to the design teams. They can then modify the design or manufacturing process to prevent the issue in future builds. For example, if a clip securing a wiring harness is found to be difficult to engage consistently, the design might be altered to make it more forgiving during installation. In essence, Suzuki's manufacturing ecosystem is a continuous conversation between design, production, and logistics. Each element shapes and supports the others, creating a tightly knit system capable of turning raw materials into road-ready cars at scale. It is this deep integration that allows Suzuki to maintain both cost efficiency and the reliability that customers expect. The creation of a Volkswagen Golf, one of the most iconic hatchbacks in automotive history, begins long before any metal is stamped or bolts are torqued. To truly appreciate the intricacy and precision of its manufacturing, we need to understand that this process represents the culmination of decades of engineering refinement, logistical coordination, and factory automation. It is not merely the assembly of components, but the orchestration of thousands of interdependent systems working in harmony, each with a dedicated role in transforming raw materials into a vehicle ready to roll off the line and onto the world's roads. The process begins at the heart of the operation, the Volkswagen manufacturing plant. One of the most famous Golf production facilities is located in Wolfsburg, Germany, where massive halls the size of several football fields stretch out in every direction. The atmosphere inside is clinical, controlled, and buzzing with quiet energy. Contrary to what one might expect, these spaces are not chaotic or deafening. They are meticulously organized, highly automated environments where human expertise collaborates with robotic precision to produce each vehicle to exacting standards. The first chapter in the physical birth of a Golf begins with the fabrication of the car's body shell. This process is commonly referred to as body in white, and it involves the welding and joining of raw sheet metal components that form the structural skeleton of the vehicle. These metal sheets typically arrive at the factory in pre-cut and coiled form, having been sourced from steel and aluminum suppliers who produce automotive-grade alloys with specific mechanical properties such as tensile strength, corrosion resistance, and energy absorption. Volkswagen has stringent quality controls on these materials, inspecting incoming shipments with laser scanners, chemical analysis equipment, and tensile testing machines to ensure that every roll meets the necessary specifications for forming and crash safety. Once approved, the metal sheets are uncoiled and fed into gigantic press machines, many stories tall, in what is known as the stamping area. These presses are a marvel in themselves, each capable of exerting thousands of tons of pressure. Using a combination of progressive and transfer dies, massive steel molds engineered to exact tolerances, these machines punch, bend, and form individual components like doors, hoods, roofs, floor panels, and side frames. Each die can weigh up to 40 tons and requires highly precise installation. The press line operates with the rhythmic certainty of a mechanical heartbeat, with each panel ejected onto a conveyor system that ferries it toward the next phase of production. From here, the stamped panels enter the body shop. This area is perhaps the most robot-dominated zone of the entire plant. Hundreds of robotic arms, painted in Volkswagen's signature orange or yellow, perform an intricately choreographed ballet of spot welding, laser welding, and riveting. These robots are guided by 3D coordinate programming and vision systems that allow them to make microscopic adjustments in real time. Their work is critical, as the dimensional accuracy of the welded body frame dictates how well later components, like the drivetrain and interior modules, will fit. The vehicle begins to take shape as floor panels are married with the side structures. Roofs are laser welded into place, and reinforcement beams are added to strengthen key impact zones. The welding robots are just one part of this highly automated process. In certain sections, human operators are still essential, particularly for tasks requiring dexterity, visual inspection, or adaptation to model variants. At these stations, workers equipped with pneumatic tools and ergonomic lifts work alongside the robots to install structural reinforcements, apply bonding agents, or verify alignment with laser-calibrated measurement systems. Every completed body shell is then run through a geometric measurement tunnel, where a series of cameras and lasers scan the surface down to the sub-millimeter level, ensuring that each vehicle conforms precisely to Volkswagen's quality blueprint. Once the body-in-white structure is completed and quality verified, the next transformative phase begins, the painting process. But before any color is applied, the raw metal body must be prepared to resist corrosion and adhere properly to the paint layers. The shell first passes through a cleaning and pre-treatment bath, typically involving a series of immersion tanks where it is cleaned of oils, particulates, and oxidation. This is followed by a process known as cathodic electrocoating, or e-coating. Here, the entire body is submerged in an electrically charged bath containing anti-corrosion primer particles. A low voltage current causes the primer to be drawn onto every metal surface, even inside closed box sections, providing complete and uniform protection. After e-coating, the body is dried in a curing oven and then transferred into the paint booths. These clean rooms are maintained at highly controlled temperature, humidity, and dust levels. The next steps involve the application of a primer layer, base coat, and clear coat, each sprayed using high-precision rotary atomizers. Robots again take the lead here, moving with fluid, sweeping motions to ensure a uniform paint film. Each coat is flash-dried between applications, and the final clear coat is cured in another high-temperature oven. Color accuracy and surface quality are assessed by specially trained technicians, often under special light tunnels that reveal even the most subtle defects or inconsistencies in the paint finish. With the painted body now cooled and cured, it proceeds to the marriage with the mechanical underpinnings, the powertrain, suspension, and chassis components. This phase marks the beginning of the general assembly process, which is one of the most logistically complex and human-involved areas of the plant. The painted body is mounted onto a continuously moving conveyor line known as the assembly line or production line, and begins its journey through a sequence of stations, each responsible for a specific set of tasks. One of the first major milestones on this line is the marriage station. Here, the body shell is carefully lowered onto a pre-assembled chassis, which includes the engine, transmission, front and rear axles, brake lines, fuel system, and other underbody modules. This process is performed using automated lifting gantries equipped with positioning sensors and torque control systems, ensuring that every bolt, mount, and fastener is attached with the correct torque specification. At this stage, precision is paramount. The alignment of engine mounts, suspension geometry, and drivetrain clearances are all verified using computer-aided fixtures and sensor feedback systems. As the car progresses down the line, workers and robots alternate in adding increasingly complex subsystems. Wiring harnesses, which have been pre-assembled in a separate part of the plant, are routed through the vehicle's interior and connected to key modules. These harnesses are essentially the vehicle's nervous system, containing hundreds of electrical wires that link sensors, control units, lighting, safety systems, and infotainment components. Routing these bundles accurately and securing them with clips, grommets, and tie wraps is both an art and a science, requiring a balance between accessibility, safety, and electromagnetic shielding. Following this, the interior components begin to enter the scene. Dashboards, HVAC units, center consoles, and infotainment displays are installed using guided insertion tools and laser alignment rigs. The seats, which are often built in a just-in-time fashion by a nearby supplier, are delivered directly to the line and bolted in place using high-torque pneumatic tools. Throughout this process, every module is scanned with a barcode reader to ensure traceability. This level of digital tracking allows Volkswagen to log the exact batch, supplier, and assembly timestamp for every major component, creating a complete digital twin of the vehicle's production history. By this point, the Golf has become instantly recognizable, with its iconic silhouette now cloaked in paint and outfitted with much of its interior. However, many critical systems have yet to be tested or activated. That next phase, electrical testing, fluid filling, and calibration, marks a turning point in the assembly process, transitioning the Golf from a mechanical object to a functioning machine. As the Volkswagen Golf continues its progression down the general assembly line, it begins to cross into one of the most critical sections of production: system initialization and functional testing. This stage transforms the vehicle from a silent shell into an electrically alive machine. It is here that the electronic control units, or ECUs, are first brought online. These digital brains govern virtually every function in the vehicle, from fuel injection timing and anti-lock braking response to climate control algorithms and sensor-based driver assistance systems. The Golf contains dozens of these ECUs, each responsible for different subsystems, and all interconnected through a series of high-speed data buses such as CAN, L-Line, and FlexRay. Before any electrical current is sent through the system, technicians connect the vehicle to a centralized factory diagnostic interface via a port located under the dashboard, the same OBD port later used by service technicians and inspection facilities. Using specialized software, factory workers upload the correct firmware and configuration data into the ECUs. This process is not merely about flashing software. It's about synchronizing every system to the specific build of that vehicle. Variables like engine type, transmission variant, lighting package, regional compliance requirements, and customer-selected options all influence how the ECUs behave. This digital handshake ensures the car will operate correctly and meet both performance and regulatory expectations. Once the ECUs are initialized, the next step is electrical verification. Automated test rigs are used to check that every connection, sensor, and actuator is functioning correctly. These rigs apply voltage and resistance checks through the wiring harness, lighting systems, and control modules. Even minor faults, such as an improperly seated connector or excessive resistance in a wire, are immediately flagged by the system. Any detected issues cause the car to be diverted from the main line to a specialized diagnostic bay where trained technicians perform pinpoint troubleshooting and rework, ensuring that no electrical faults go undetected. Parallel to the electrical system bring-up, the vehicle also receives its initial fill of operational fluids. These include engine oil, coolant, brake fluid, transmission fluid, power steering fluid if hydraulic, and in some cases, refrigerant for the air conditioning system. The filling process is performed by robotic dispensing arms that are pre-programmed to deliver the precise volume and type of fluid required for each model. Flow meters, pressure sensors, and digital records ensure absolute consistency and prevent underfilling or contamination. The fuel tank is also filled with a small amount of test fuel, typically around 5 to 10 liters, sufficient for initial startup, emissions testing, and short-range driving tests later in the process. After fluid filling, one of the most dramatic moments in the assembly process occurs: the engine start. This is not done casually, nor is it done without extensive prior checks. Once all systems are confirmed ready, a technician activates the ignition via the factory diagnostic system or a standard key fob, causing the engine to turn over for the first time. Sensors throughout the vehicle immediately begin transmitting data: engine RPM, oil pressure, coolant temperature, voltage levels, and emission sensor feedback, all of which are monitored live by quality assurance software. If the engine does not start within a certain time window, or if any critical values fall outside the permissible range, the vehicle is automatically flagged for further inspection. Assuming a successful startup, the next phase involves dynamic system checks. These include actuating key mechanical subsystems to ensure proper functionality. The steering is rotated lock to lock to test assist levels and detect any binding. The brakes are pressurized to confirm pedal feel and hydraulic integrity. The transmission is cycled through its gears, with automatic models shifting through each range while stationary, and manual models undergoing clutch engagement tests. Additional functions like power windows, central locking, infotainment screens, headlight alignment, and mirror adjustments are also verified at this stage. All of these checks are conducted on the moving assembly line or at dedicated inspection stations known as end-of-line testers. These stations are equipped with rollers, sensors, cameras, and feedback terminals that allow technicians to observe live data streams. If a vehicle passes all of these checks, it is allowed to proceed to the next major step: wheel mounting and torque application. At this point, the Golf receives its wheels and tires, which have been assembled and balanced in a separate part of the plant. Tire suppliers often work in close partnership with the assembly plant, sometimes even maintaining satellite facilities on site to deliver tires in real time according to the production sequence. The wheels are mounted using robotic arms equipped with torque sensing screwdrivers. These tools are programmed with model-specific torque settings and follow a defined tightening sequence to ensure that every lug nut is fastened uniformly, reducing the risk of vibration or uneven stress on the brake rotors. After wheel installation, the vehicle is lowered off its assembly jigs and finally touches the ground under its own weight. This moment, often called first contact, marks the vehicle's readiness for dynamic testing. It is now fully assembled, fully functional, and ready to move under its own power. But production does not end here. The vehicle is then driven, slowly and under tight controls, to the next area of the plant: the rolling road test bench, also known as the dynamometer station. Here, the car is placed onto a set of rollers that simulate driving conditions while keeping the vehicle stationary. The purpose of this test is to perform a full-spectrum functional evaluation under load. The vehicle is accelerated, decelerated, and driven at varying speeds, while sensors record engine performance, emissions output, braking effectiveness, and drivetrain behavior. Advanced vision systems check headlight aim and beam shape. Microphones measure cabin noise under acceleration. Even the wiper system is tested using artificial rainfall nozzles while the car is driven at simulated speeds. If any aspect of this test fails to meet Volkswagen's internal benchmarks, the car is again pulled from the line and sent to a rework zone. Here, highly trained specialists diagnose and resolve the issue, whether it be a misaligned sensor, a software glitch, or an out-of-spec component. Vehicles cannot proceed to final inspection until they achieve a perfect score on the dynamometer test. Following this dynamic validation, the car enters the final quality inspection area. This zone is brightly lit and staffed with quality control inspectors who perform a visual and tactile examination of every surface, seam, and feature. Paintwork is scrutinized under color-correct lighting to detect any blemishes, orange peel, or dust inclusions. Door gaps and panel alignment are measured with precision gauges. Interior materials are checked for fit, finish, and correct placement. Inspectors open every door, operate every switch, and sit in the car to check for rattles, uneven padding, or installation errors. This is often the first time someone interacts with the Golf as a complete product, and every detail matters. Once the vehicle passes its final inspection, a protective wrap is applied to its most vulnerable surfaces, typically the hood, roof, mirrors, and door edges, to prevent damage during transport. Barcodes and shipping labels are affixed, and the vehicle is driven to the logistics yard, where it joins a massive fleet of completed Golfs waiting for shipment. These yards are organized with incredible precision, with each car's location digitally tracked for efficient loading onto transport trucks or rail cars. While this marks the end of the physical assembly process within the factory walls, the story of each Golf is far from over. It now enters the distribution and logistics phase, a sprawling global network designed to deliver each vehicle to its final destination as quickly and safely as possible. But that segment of the journey involves a separate layer of logistical planning, international coordination, and dealership preparation, all of which merit a detailed explanation of their own. The freshly assembled Volkswagen Golf, now cloaked in its protective transport films and validated through layers of mechanical, electrical, and aesthetic inspections, begins its transition out of the factory environment and into the broader world. This stage, the post-production logistics and distribution process, is a sophisticated dance of real-time tracking, intermodal transportation, and region-specific compliance, all of which are critical to ensuring that each vehicle reaches the correct dealer in the correct configuration and in pristine condition. After final inspection, the Golf is driven from the assembly line to the Vehicle Logistics Center, often located adjacent to the main manufacturing facility. Here, trained drivers guide the vehicles along designated internal roads, maintaining low speeds and following strictly mapped routes to avoid cross-contamination or accidental damage. At the staging yard, vehicles are sorted based on destination markets, production variants, and transport mode. Some will head to domestic dealerships via truck, while others will be loaded onto trains for long-haul land journeys. For global markets, many Golfs are prepared for shipping by sea, making their way to port via specialized car-carrying rail networks. Before any Golf leaves the staging yard, a final scan is performed. Using handheld barcode scanners or RFID readers, workers verify the vehicle's unique VIN, vehicle identification number, against the factory's production records. This cross-referencing ensures that the car has passed all necessary quality gates, has been matched with the correct transportation order, and is headed to the appropriate regional hub. Additionally, certain destination countries require extra compliance steps before a vehicle can legally enter or be registered, such as emissions documentation, safety certification, or region-specific firmware updates to the vehicle's ECUs. These requirements are embedded into the logistics planning software, and vehicles are automatically routed to compliance zones where technicians apply the necessary updates or decals before departure. Once verified and queued, the Golf is prepared for loading onto a transport carrier. For truck transport, specialized vehicle haulers equipped with multi-level ramps are used. These carriers are engineered to accommodate various vehicle sizes while maximizing capacity and maintaining balance for road stability. Loading is conducted with extreme care. Each car is driven up ramps and secured using wheel straps, chocks, or integrated platform locks that prevent movement during transport. Drivers are trained not only in vehicle handling, but also in load balancing, ensuring that the distribution of weight across the trailer complies with legal road limits and mechanical tolerances. For long-distance rail transport, the Golf is moved onto enclosed or open-sided car transport wagons. These wagons can hold up to a dozen vehicles per unit and are designed to withstand the rigors of long-haul journeys across multiple climate zones. Rail is favoured for its cost efficiency and environmental impact, particularly for routes within Europe, where dense rail infrastructure allows cars to be delivered to regional distribution centres with minimal handling. Once the vehicles reach their destination hubs, often located just outside major cities, they are transferred to final mile delivery trucks that ferry them to individual dealerships. When the Golf is destined for international markets outside of Europe, such as North America, Asia, or Australia, it must be transported by sea. This requires loading the vehicles onto large roll-on/roll-off cargo vessels, also known as ro-ro ships. These enormous ships are essentially floating multi-story parking garages, capable of holding thousands of vehicles at once. At the port terminal, cars are driven aboard by logistics personnel who work under tight schedules to fill each ship efficiently. Vehicles are parked according to a precise digital manifest, which maps each car's location by deck, row, and position for accurate unloading at the destination port. Ro-ro shipping requires a high level of environmental control. Vessels are designed to maintain safe humidity levels, minimize exposure to salt air, and prevent the movement of cars in rough seas through a system of tie-down points and loading jacks. Once the vehicle arrives in its destination country, it goes through a process known as port processing. This includes customs clearance, regulatory inspections, and any market-specific modifications. Depending on the country, this might involve the installation of alternative language infotainment software, the addition of local safety equipment like fire extinguishers or first aid kits, or the application of region-specific emblems and badges. Vehicles are once again inspected for transport-related damage, cleaned, and detailed before being sent to the dealership. But while distribution is an essential part of the car's journey, it is merely the final chapter in the broader industrial narrative. To truly understand the full scope of how a Volkswagen Golf comes to be, we must look beyond the visible car to the invisible infrastructure that supports its manufacture, the supplier network, component fabrication, and just-in-time logistics that converge at the assembly plant, like veins feeding into a living heart. Every Golf is made up of more than 30,000 individual parts, many of which are produced not by Volkswagen directly, but by a web of Tier 1 and Tier 2 suppliers across the globe. These include suppliers specializing in electronics, seats, glass, tires, injection molded plastics, turbochargers, radiators, axles, and much more. These companies operate under strict quality and timing requirements, often working within a just-in-sequence framework. This means that not only must the parts arrive just in time to avoid stockpiling or shortages, but they must also arrive in the exact order in which they are needed on the line. To enable this, Volkswagen uses a combination of supplier parks, regional distribution centers, and digital planning tools that forecast production demand down to the minute. Many of these suppliers operate satellite facilities on or near the Volkswagen campus itself. These microfactories are tightly integrated into the main production loop. For instance, a seat supplier may receive a digital order moments after a car body is painted and matched to a particular trim level. Within hours, the seat is built, quality checked, and delivered to the assembly line just as the car arrives at the station where it will be installed. The just-in-time system dramatically increases efficiency and reduces warehousing costs, but it also demands precision and resilience. Any disruption in the supply chain, whether due to weather, labor issues, or global events, can ripple across the production schedule. To manage this complexity, Volkswagen employs advanced manufacturing execution systems and enterprise resource planning software that communicate with suppliers, forecast demand, and adjust schedules in real time. Each supplier must adhere to predefined quality protocols, including statistical process control, failure mode analysis, and traceability documentation, which are routinely audited by Volkswagen's internal teams. On the component level, many key parts are manufactured using highly specialized processes before they ever reach the main assembly line. Take, for example, the engine, the mechanical heart of the Golf. Engine blocks begin their life as raw aluminum or cast iron, melted and poured into precision molds using high-pressure casting methods. Once solidified and cooled, the blocks are machined using CNC equipment that drills, hones, and surfaces the bores and mating faces to tolerances often measured in microns. Crankshafts, camshafts, pistons, and cylinder heads undergo similar processes, each passing through multiple heat treatment, grinding, and quality inspection stages before final assembly. The completed engine is then mated with its transmission, tested on a cold bench, a fixture that simulates operation without fuel or combustion, and sent to the main production hall. There, it joins the sequence of drivetrain assemblies that will eventually meet their respective body shells on the marriage line. Similarly, high-tech components like digital dashboards, ADAS sensors, and infotainment head units are built and tested in cleanroom environments to prevent contamination or electrostatic damage. These electronic assemblies are subjected to functional tests, environmental stress simulations, and firmware updates before being sent to the main line. At the plant level, all of these moving parts, mechanical, logistical, and digital, converge into what is often described as a cyber-physical production system. Assembly lines are increasingly governed by AI-enhanced predictive analytics, machine learning algorithms that forecast wear on machinery, and autonomous material handling vehicles that navigate factory floors using LiDAR and GPS. Real-time dashboards allow factory managers to monitor production flow, equipment uptime, part inventories, and worker ergonomics from centralized control centers. Robots, collaborative arms known as cobots, and human workers form a hybrid workforce that constantly adapts to changes in demand, variant complexity, or technological updates. All of this results in a manufacturing ecosystem that is as complex and finely tuned as the vehicles it produces. The Volkswagen Golf, which might appear to the average buyer as a simple compact hatchback, is in reality the output of a global network of suppliers, engineers, robots, and logisticians working in concert with millisecond-level precision. It is a product born of thousands of hands and millions of decisions, every one of them contributing to the moment when the car's engine starts for the first time, the headlights blink to life, and it begins its journey toward the showroom floor. As the story of the Volkswagen Golf continues within the factory walls, we now shift focus to the critical yet often overlooked phase that follows the assembly and functional testing of the physical vehicle. Final calibration, detailed software programming, and human-centered quality control measures that ensure not just mechanical soundness, but also driving experience fidelity, safety compliance, and brand consistency. This stage marks the final opportunity for engineers and technicians to refine the car's personality, the way it feels, sounds, and responds before it ever reaches a dealership. Once the vehicle passes its rolling road test, electrical verification, and cosmetic inspections, it enters what's referred to in modern manufacturing as the calibration and personalization loop. Here, technicians interface with the vehicle's multiple electronic control units, upwards of 50 in many Golf variants, to fine-tune parameters such as steering weight, throttle response, transmission shift points, air conditioning behavior, and even ambient lighting modes. Although these parameters are based on predefined model profiles, small adjustments are often needed to account for tolerances in component performance, environmental conditions, and the specific variant configuration of the vehicle. This process uses a digital toolchain, often referred to as a centralized vehicle configuration system. The technician connects a specialized programming console to the vehicle's onboard diagnostics port. Through this interface, the system retrieves the vehicle's build sheet, a digital summary of every major component, trim level, engine type, and region-specific setting installed during production. Based on this, The technician downloads the relevant firmware packages and configuration profiles from a secure Volkswagen server. These files include calibrations for dynamic systems like ESC, lane keeping assistance, adaptive cruise control, and the steering rack's servo control logic. The software installation itself is performed with high redundancy and validation steps. Each module receives a cryptographic checksum, ensuring the integrity of the code after download. The system then runs a diagnostic sweep, verifying that all ECUs are correctly communicating across the vehicle's CAN and LN bus architecture. Should any module fail to respond or report a checksum mismatch, the vehicle is flagged and removed from the main line for specialized reprogramming in a secure rework area. This level of rigor is necessary, not only to ensure reliability and drivability, but also because these software systems control functions directly linked to passenger safety. Following calibration, the vehicle passes through a sequence of human-led evaluations known internally as sensory audits. In a world increasingly governed by automated inspection and robotic precision, this human touch remains indispensable. Sensory audit teams, often composed of master technicians and experienced inspectors, evaluate things that machines cannot easily quantify. They listen for rattles or unexpected noises while operating various components, apply gentle force to test the feel of buttons and switches, and run their hands along upholstery seams to detect imperfections in fit or material finish. These teams test the firmness of seat padding, assess the resistance in climate control knobs, and verify the damping in the glove box lid's opening motion. This inspection process is not random. Each inspector follows a detailed checklist created for the Golf's specific variant, whether it's a base TSI model or a performance-oriented GTI. Every tactile point of interaction with the driver or passenger is scrutinized. The sound of the door closing, the feedback of the turn signal stalk, the clarity of the infotainment screen. Even the air vents are examined for smooth adjustability and structural integrity. These subtle, almost imperceptible qualities play a vital role in shaping customer perception. They influence whether a driver describes the Golf as solid, refined, or thoughtfully engineered. And Volkswagen knows that these sensory markers directly translate to brand loyalty. Parallel to the sensory audit is a final high-pressure water test. Here, the vehicle is driven into a sealed chamber where it is subjected to a simulated rainstorm, complete with directed nozzles spraying water at high pressure from multiple angles. The goal is to identify leaks around door seals, windshield bonds, taillights, and underbody grommets. As the water jets barrage the vehicle, sensors inside the cabin monitor for moisture ingress, while technicians inspect areas with flashlights and absorbent strips to detect even minute amounts of seepage. Any vehicle that fails this test is returned to a specialized sealing and bonding repair zone where issues are addressed before retesting. Once these final inspections are complete, the vehicle is officially released from production. However, in a modern Volkswagen plant, this release is also the beginning of a data-rich archival process. A complete digital profile of the vehicle, from every torque specification logged during assembly, to the paint batch number, to the firmware version of the braking system, is uploaded to a central database. This digital twin acts as a permanent reference for the vehicle throughout its service life. If a recall or service bulletin is ever issued in the future, this record allows Volkswagen to identify not only which vehicles are affected, but precisely what components or subsystems were installed and when. It is also worth noting that many Golf variants are produced with advanced driver assistance systems, which require a final calibration procedure using sophisticated optical targeting tools. This is especially critical for features like lane keeping assistance, traffic sign recognition, autonomous emergency braking, and adaptive cruise control, which rely on a front-facing camera, radar sensors, and sometimes LiDAR. These sensors must be calibrated in relation to the car's central axis, suspension height, and tire circumference. The calibration process is performed in a controlled bay using visual markers, checkerboard targets, and reference panels, positioned at known distances. Specialized software then guides the technician through alignment adjustments and performs a verification routine, simulating input data to test the system's reactions. The factory also considers the growing importance of software updates throughout a vehicle's lifecycle. Increasingly, Golf models are being built with over-the-air update capabilities. This means that certain vehicle functions can be improved or corrected remotely without visiting a dealership. To enable this, each vehicle must be registered with Volkswagen's secure update server and fitted with a telematics control unit capable of handling encrypted data downloads. Before leaving the plant, the vehicle undergoes a brief connectivity test using a private cellular or Wi-Fi network. This ensures that the vehicle can receive updates in the field and that the security keys assigned during factory programming are valid and authenticated. Another major focus of final stage production, particularly in recent years, is environmental sustainability. Volkswagen has implemented comprehensive measures to reduce the ecological footprint of Golf manufacturing. For example, paint shops, traditionally among the most energy-intensive and pollutant-heavy parts of vehicle production, now use water-based paints and advanced overspray capture systems to reduce volatile organic compound emissions. Waste heat from ovens and drying tunnels is recovered and recycled into the factory's climate system. Water used in the electrocoating and wash booths is treated on-site and reused in a closed-loop system. Powering the factory itself is a growing area of environmental emphasis. Many of the plants where the Golf is manufactured have transitioned to renewable energy sources, such as wind or hydroelectric power. In Wolfsburg, for instance, Volkswagen has partnered with regional utilities to supply the production lines with green electricity. Additionally, automated lighting, motion sensors, and energy-efficient drive systems on robots and conveyors contribute to reduced overall consumption. These investments not only lower the per-vehicle carbon output, but also align with Volkswagen Group's broader Way to Zero strategy, a commitment to climate-neutral mobility and carbon-neutral production by 2050. Within the plant, materials management is handled with sustainability in mind as well. Steel and aluminum scrap generated during stamping operations are carefully sorted, compressed, and sent to recycling centers, some of which are reintegrated back into the supply chain. Plastics from production offcuts or rejected trim parts are ground down and reused in non-visible components. Even packaging materials used to deliver parts, such as crates, dividers, and protective films, are tracked and returned to suppliers in a closed-loop logistics model. What makes the Volkswagen Golf's production so remarkable is not just the car itself, but the systems, philosophies, and technological ecosystems that produce it. Each vehicle embodies the cumulative effort of thousands of hours of engineering, years of supplier relationships, terabytes of design simulations, and millions of precisely orchestrated manufacturing movements. What rolls off the line is not a standalone product, but the physical representation of a global, highly optimized industrial organism. One designed to balance quality, efficiency, innovation, and sustainability in every nut, panel, circuit, and drop of fuel or electricity it consumes. As we move deeper into the Volkswagen Golf's manufacturing story, we begin to explore the systems behind the systems, the cutting-edge technologies and organizational strategies that elevate Golf production beyond traditional automotive assembly. Much of this innovation centers around Volkswagen's use of modular platforms, intelligent factory automation, and advanced data analytics all of which have transformed not just how a Golf is made, but how efficiently, flexibly, and sustainably it can be produced, alongside a range of other vehicle models. At the core of this evolution is Volkswagen's MQB platform, short for Modulare Kurbaukasten, which translates to Modular Transverse Matrix. Introduced in the early 2010s, this platform underpins not only the Golf, but also a wide range of vehicles across Volkswagen Group's brands, including the Audi A3, Seat Leon, and Skoda Octavia. The brilliance of the MQB platform lies in its standardized architecture. Critical hard points, such as the position of the engine, the distance between pedals and front axle, and mounting locations for crash structures, are fixed across models, while allowing flexible variation in wheelbase, track width, and body style. This enables massive economies of scale and allows the Wolfsburg plant, among others, to produce multiple models on a single line with minimal retooling. In practice, this means that a Golf might be built on the same line as a Tiguan or a Touran, using many of the same robotic stations, fastening tools, and software configurations. Tooling carts, parts bins, and robotic arms are designed with adaptability in mind. Instead of having separate jigs for each model, multifunctional fixtures and programmable robots detect the incoming body type via RFID tags or QR codes and adjust themselves in real time. A welding robot, for example, might apply different sequences or torque levels, depending on whether it is working on a Golf hatchback or a longer wheelbase estate model, all without human intervention. This production flexibility is supported by a sophisticated manufacturing execution system, a digital nervous system that tracks every car's status as it moves through the factory. Each vehicle is assigned a digital build order, stored in a centralized database and updated in real time. This build order contains detailed instructions for every station: which components to install, what software to flash, how to calibrate sensors, and which quality checks to perform. At each workstation, screens display the relevant data for the technician or robot, and barcode or RFID scanners confirm that the correct parts are being used before the system allows the job to proceed. The use of artificial intelligence and machine learning is increasingly embedded into this ecosystem. For instance, predictive maintenance systems monitor vibration, temperature, and performance data from thousands of robots, conveyors, and tools in real time. If a welding robot's arm begins to show early signs of wear, even imperceptible to human operators, the AI flags the issue and schedules preventative maintenance before failure can occur. This predictive approach significantly reduces downtime and helps maintain the tight production cadence that modern car manufacturing demands. Another area where AI plays a pivotal role is in vision systems and quality control. High-resolution cameras paired with deep learning algorithms are used throughout the assembly and inspection processes. These systems are trained on thousands of images to identify correct panel alignment, paint consistency, weld seam quality, and even minute cosmetic defects. In the paint shop, for example, the system can detect a single dust particle trapped in a clear coat, then alert technicians to isolate the cause, whether it's an air filtration issue, static charge on the body panel, or improper cleaning upstream. These insights are logged and used to refine both the hardware and the process over time, feeding back into a continuous improvement loop. But AI is not just about machines replacing human oversight, it's about augmenting human decision-making. In interior assembly, where more variation exists due to trim-level complexity, workers are assisted by augmented reality headsets that project assembly instructions directly into their field of view. These AR systems highlight where each clip, fastener, or electrical connector should go and can overlay 3D models of correct placements onto the physical work area. If the system detects a potential mismatch, such as a left-hand drive HVAC control unit being installed in a right-hand drive model, it alerts the worker before the part is fully installed. This not only reduces errors, but empowers technicians to handle more complex tasks without relying solely on memory or printed documentation. All of these advancements contribute to a concept Volkswagen refers to as smart production, an overarching philosophy that treats the factory not as a static facility, but as a living, evolving system. This philosophy is particularly evident in how Volkswagen manages its energy consumption, materials flow, and human ergonomics. For example, autonomous guided vehicles have largely replaced traditional forklifts and trolleys in many areas of the Golf's production. These AGVs navigate using a combination of magnetic strips, LiDAR, and real-time mapping, delivering parts from storage zones to the assembly line on demand. This reduces congestion, minimizes human error in part selection, and allows the line to adapt more fluidly to shifting production priorities. From an energy standpoint, smart production integrates intelligent building management systems that adjust heating, cooling, and lighting based on real-time occupancy and environmental data. Robots enter standby mode when idle for more than a few seconds. Compressed air systems, traditionally one of the most energy-intensive parts of any industrial plant, are monitored by AI that optimizes pressure delivery to exactly what is needed, exactly where it is needed, with zero excess. These micro-optimizations, when multiplied across thousands of systems and millions of cycles per year, contribute to measurable gains in sustainability. Ergonomics and human factors are also key to this philosophy. Every workstation on the Golf assembly line is designed to reduce strain, fatigue, and injury. Adjustable platforms allow workers to bring the vehicle to an optimal height depending on the task. Overhead, assist arms support the weight of heavy tools, reducing the need for muscle force. Color-coded part trays, automatic torque wrenches, and real-time feedback screens help workers maintain quality while minimizing the mental load of memorizing dozens of process steps. Additionally, Volkswagen invests heavily in worker training, offering digital simulators, VR-based assembly previews, and rotating task assignments to improve skill versatility and maintain high morale. This combination of human-centered design and intelligent automation also allows the Golf production line to be highly responsive to changing market demands. If a sudden spike in orders for a particular trim level occurs, say the Golf GTI with a sunroof and adaptive suspension, the MES system can reprioritize the build queue, notify suppliers of increased part demand, and adjust the workstations along the line in real time. Robots recalibrate their movement patterns, AGVs update their delivery routes, and workers are presented with new instructions through their digital displays. What once would have required days or weeks of retooling now happens in hours, or in some cases, minutes. One of the most compelling outcomes of these systems is Volkswagen's ability to maintain quality parity across global production sites. Thanks to centralized data systems, a Golf built in Wolfsburg can be virtually identical in build quality and performance to one assembled in Puebla, Mexico, or Changchun, China. Volkswagen uses digital twins of its production equipment, virtual replicas that simulate and mirror real-world machines, to replicate best practices across all facilities. If a process optimization is discovered in one plant, such as a more efficient adhesive application method or a faster sensor calibration routine, that improvement can be tested digitally, validated, and then rolled out to other sites via secure updates to their MES software. All of these advancements are not just about building a better car. They're about building a better manufacturing system, one that is scalable, adaptable, and forward-compatible. This is especially important as the automotive industry transitions to electrification. The Golf, as of the latest generation, shares many of its production processes with Volkswagen's ID family of electric vehicles. While the ID.3 and ID.4 are built on a separate platform, MEB. The lessons learned from MQB production, including robot versatility, flexible logistics, and digital calibration, are directly transferable. In fact, many stations within the same factory can now switch between building a combustion engine Golf and an electric vehicle, with only minor tooling changes and software adjustments. Volkswagen's approach to production is ultimately one of modular intelligence, a blend of standardized hardware, reconfigurable software, and scalable systems that can evolve with the demands of new technologies, consumer preferences, and global regulatory changes. And in this sense, every Golf rolling off the line is not just a vehicle. It's a node in a vast, intelligent, and continually learning machine. Before the hum of torque wrenches or the hiss of pneumatic arms ever begin their synchronized dance, the production of a Freightliner truck starts much earlier, at the material level. Freightliner, as a brand under Daimler Truck North America, sources its materials globally, but manufactures domestically with an emphasis on high efficiency, high quality, and lean production methodologies. In practice, that means every component, from the massive frame rails to the smallest electrical connectors, follows a strict protocol from the moment they're commissioned. The backbone of every Freightliner truck is its chassis, and that begins with the steel. High-strength, low-alloy steel, engineered specifically to provide structural rigidity while reducing weight, is delivered in massive coils or long billets. These raw materials are typically sourced from certified mills across the US and Canada. Each shipment comes with metallurgical certification to ensure the proper carbon content, tensile strength, and fatigue resistance required for heavy load applications. Once the steel arrives at the plant or designated fabrication facility, it undergoes an initial inspection. Visual checks confirm the absence of surface defects like lamination or rust, while ultrasonic sensors or X-ray systems may be used for internal flaw detection. From there, the steel enters the cutting phase. Frame rails, the long backbone beams of the truck, are precision cut using CNC plasma or laser cutting systems. These machines follow CAD-generated paths to carve out the exact dimensions needed, often with tolerances down to fractions of a millimeter. Automated feeders load each steel section onto rollers, feeding them beneath gantry-style cutting heads. Sparks fly, not chaotically, but in orchestrated arcs of heat and light, as the steel begins to take its first identifiable form. But cutting is just the beginning. Each cut rail or cross member must be drilled, beveled, and punched to accommodate brackets, wiring looms, and other structural elements. These are done using robotic drill stations and multi-axis milling centers, often clustered in work cells that operate semi-autonomously. Workers oversee quality and handle any exceptions flagged by the system. It's not uncommon for a single frame component to pass through 8 or more stages of fabrication before it's ready for assembly. Meanwhile, in a different part of the facility, or sometimes an entirely different Tier 1 supplier plant, other key components begin their own parallel journeys. The cab, for instance, which forms the command center for the driver, starts its life as a series of stamped metal panels. These are formed in high-tonnage stamping presses, where flat steel sheets are fed into dies that exert upwards of 2,000 tons of pressure to form complex three-dimensional shapes. Roof panels, sidewalls, floor pans, and door skins are pressed, trimmed, and then moved into assembly cells for robotic welding. In one of the most mesmerizing stages of production, robotic arms, each about the size of a small car, move in choreographed unison, welding dozens of seams with astonishing precision. These are spot welds, placed at strategic structural points identified through finite element modeling simulations, ensuring the cab can withstand torsion, vibration, and frontal impact forces. The welding jigs are precisely machined, holding the panels in a fixed position to prevent warping and maintain dimensional accuracy. Each weld is logged, and sensors on the welding arms monitor heat, duration, and penetration in real time, ensuring every seam meets exacting standards. Once the skeleton of the cab is complete, it moves on to the paint line, though it's not quite time for color yet. First, the cab shell undergoes a rigorous cleaning and pre-treatment process to prevent corrosion and promote paint adhesion. This includes an alkaline wash to strip oils and residues, followed by a zinc phosphate bath that chemically prepares the metal. After that, the cab is electrocoated. In this process, the entire cab is submerged into a tank filled with electrically charged paint particles. A voltage is applied, causing the paint to be uniformly attracted to every surface, even inside the seams and cavities. This e-coat layer is critical. It forms a rust-resistant shell that will protect the truck for years, even in the harshest environments. While the steel skeletons are being formed and treated, the plastic and composite parts that will furnish the truck's interior and aerodynamic exterior begin their own fabrication process. Instrument panels, bumpers, fender extensions, and fairings are typically made using injection molding. Heated polymer resin is injected into steel molds under high pressure, then cooled and ejected, forming parts that are lightweight, durable, and dimensionally stable. These components are trimmed, drilled, and sometimes pre-painted before being cued for final assembly. The engine, the heart of the Freightliner, is usually sourced from Detroit Diesel, another subsidiary under the Daimler Truck umbrella. Engines such as the Detroit DD13, DD15, or DD16 are manufactured in parallel production lines, where aluminum engine blocks are cast, machined, and built up through a layered process involving crankshaft installation, piston assembly, cylinder head mounting, fuel system integration, and finally the addition of sensors, electronic control modules, and turbochargers. Each engine undergoes a hot test, where it's fired up and run under load conditions before it ever ships to the truck assembly plant. Transmissions and axles, often sourced from Eaton or Detroit Axle, are built in similar fashion, tested, and then sent in just-in-time batches to the Freightliner facility. Inventory control is tightly managed. Freightliner follows a lean manufacturing strategy, meaning parts arrive in closely timed windows based on actual production schedules. This minimizes storage needs on site and keeps the factory floor clear and efficient. By now, dozens of subsystems are in progress across multiple areas. Wire harnesses are being measured, cut, and terminated using automated cable cutting machines. Instrument clusters are assembled on dedicated benches with modular electronics, and HVAC systems are pre-tested on standalone rigs. Even the seats, often custom ordered based on customer specifications, are being upholstered, stitched, and fitted with safety sensors and air ride mechanisms. Each of these elements, whether it's a 900-pound axle or a palm-sized switch, will soon converge on a single assembly line, but that's still to come. First, all subcomponents must undergo quality control checks. Engineers and inspectors use a mix of digital calipers, laser measuring systems, and coordinate measuring machines to verify dimensions. Electrical systems are continuity tested using automated probes, while air and hydraulic systems are pressure tested for leaks. Any deviation from spec is logged in a centralized manufacturing execution system, or MES, which tracks every part from cradle to completion. The MES is the digital backbone of Freightliner's production philosophy. Every cab, frame, and engine has a digital birth certificate, a file that accumulates every test, measurement, and torque spec as it moves through the line. This level of traceability allows Freightliner to not only ensure consistent quality, but to rapidly isolate and correct defects if issues ever arise in the field. At this point, with thousands of parts flowing in from dozens of stations, the stage is set. The real magic, the assembly line itself, is about to begin. This is where human skill and machine precision merge in a seamless ballet of bolts, wires, and rivets, where every 12 minutes, a completed Freightliner truck rolls off the line, ready to shoulder the burden of logistics across a continent. But the choreography that makes that happen is anything but simple. As the curtain rises on the main assembly line, the factory enters its most synchronized and visually striking phase. The rhythm of production is guided by what's known in manufacturing as tak-T time, the calculated beat that determines how long each station has to complete its task. For Freightliner, depending on the model and plant configuration, a new truck might be rolling off the line every 10 to 15 minutes. But behind each of those trucks is a sequence of over 500 carefully choreographed steps involving hundreds of skilled workers and dozens of robotic assist systems. It all begins with the bare chassis rails, two long beams of hardened steel that form the skeletal spine of the truck. These rails arrive from the fabrication zone on heavy-duty conveyor systems. Before they even reach the first assembly station, they are scanned for orientation, Idaho, verified via barcode, and inspected by vision systems to ensure all required holes, cuts, and fasteners are present. Then, they're placed onto mobile build carriers, massive, gear-driven fixtures that move the entire truck frame down the line at a precise, constant pace. These carriers can rotate and tilt the frame slightly, allowing technicians ergonomic access to areas that would otherwise be difficult to reach. The first phase of assembly is focused on the undercarriage, namely installing the axles, suspension systems, cross members, and mounting brackets. A fully loaded Freightliner may be designed to support up to 80,000 pounds of gross vehicle weight, so the frame must be fortified to handle these loads with absolute reliability. Workers install steel cross members, bolted or riveted perpendicular between the chassis rails, to enhance structural rigidity and prevent torsional twisting. Next comes the installation of the front and rear axles. Depending on the model, this could be a tandem axle configuration or a single drive axle for lighter duty vocational trucks. Each axle, pre-assembled with hub bearings, brake components, and wheel ends, is hoisted into place by overhead gantries equipped with hydraulic grippers. These assistive lifting devices are guided by technicians who carefully lower the multi-ton axle into position beneath the chassis rails. Once aligned, brackets and U-bolts are torqued down using calibrated pneumatic tools, each fitted with torque sensors to ensure fasteners meet the manufacturer's precise specifications. At the same time, the suspension system is installed. For most long-haul Freightliners, this means an air suspension setup where heavy-duty airbags, connected to leveling valves, are mounted in tandem with shock absorbers and trailing arms. These systems are designed to not only provide a smoother ride for the driver, but to protect the cargo from vibration and impact damage over long distances. Airlines are routed and clipped into place, and the system is pre-pressurized to check for leaks and integrity before moving to the next station. The steering system, too, is beginning to take form at this stage. Steering gearboxes are bolted to the frame and connected via linkages to the front axle. These components, although not yet connected to a steering wheel, are functional and mechanically aligned. Meanwhile, brake lines, often color-coded and routed through stainless steel conduits, are laid out along the chassis and secured at regular intervals. These lines will eventually connect to air reservoirs and electronic braking modules, which will manage the truck's braking system with a combination of mechanical and computer-assisted precision. As the frame grows in complexity, so too does the pace of integration. Fuel tanks are installed using insulated saddles and steel straps. These tanks, usually aluminum for weight savings, are pre-tested for leaks before arriving at the line. DEF tanks, used in modern emissions systems for diesel engines, are added alongside them. In vocational trucks like dump trucks or cement mixers, auxiliary hydraulic systems may also begin installation at this point, including reservoirs, pumps, and control valves. While this underframe activity unfolds, the cab is progressing down a parallel sub-assembly line. The painted cab shell, fully E-coated and prepped, is moving through its own series of workstations where interior components are being added. First, the wiring harnesses, pre-assembled bundles of electrical cable with color-coded insulation and printed tags, are laid into place. These harnesses control everything from the instrument cluster and lighting to the HVAC system and advanced driver assistance systems. Next, the dashboard is installed. This large composite structure comes pre-populated with electronic modules, venting ducts, and sometimes even gauge clusters, depending on the configuration. The HVAC unit, assembled separately and pre-tested in an environmental chamber, is mated behind the dash with refrigerant lines and vacuum-actuated dampers. Meanwhile, sound insulation panels are installed across the firewall and floor pan. These include layered composites of foam, mass-loaded vinyl, and aluminum shielding to reduce road and engine noise in the cab. Seats are installed next. Air ride driver seats with integrated heating, lumbar support, and, in some cases, electronic adjusters. These are bolted into pre-threaded inserts in the cab floor, and once secured, connected to wiring and air supply lines. Overhead control panels, sun visors, storage compartments, and sleeper modules begin assembly as the cab continues moving. Even interior trim pieces, such as door panels, kick plates, and A-pillar covers are clipped into place at this point. Every screw, every clip, every surface must pass tactile and visual inspection by quality technicians trained to detect the slightest deviation. With the cab interior nearly complete and systems verified for fit and function, it's now ready for what's known as the cab-to-chassis marriage. This is one of the most complex and dramatic moments in the entire production sequence. The cab, hoisted on a precision gantry crane, is slowly lowered onto the rolling chassis. But this isn't a blind placement. Alignment pins, laser positioning sensors, and human guides all play a role in ensuring the cab lines up perfectly with mounting points, firewall openings, and wiring pass-throughs. As the cab settles onto its mounts, typically a mix of rigid and elastomeric bushings to absorb vibration, technicians bolt it down using automated torque tools. Simultaneously, they connect the main electrical interface harnesses between the cab and chassis. These waterproof, high pin count connectors handle everything from turned signals and headlamps to engine controls and CAN bus data networks. Airlines for the braking and suspension systems are also routed from the chassis bulkhead into the cab via quick connect fittings. The steering column is connected to the steering gear via a collapsible intermediate shaft, and the parking brake cable is attached to its actuator. At this point, the truck is now beginning to resemble its final form. The integration of cab and chassis transforms a scattered system of components into a singular, rolling vehicle platform. And with this critical milestone complete, the truck moves into the fluid fill and powertrain test zones. But before that, another major piece must be installed: the engine and transmission assembly. Unlike consumer vehicles, where engines are often installed early in the process, Freightliner trucks receive their fully dressed engines after the chassis is partially assembled. The engine transmission module arrives as a single unit, mounted on a subframe, complete with turbochargers, accessory drives, exhaust manifolds, and cooling modules already attached. This assembly is lifted into place using robotic hoists, aligning with the engine cradle on the chassis. Mounting bolts are inserted and torqued down in a specific sequence to prevent frame distortion. The drive shaft, a multi-section tube with U-joints and center bearings, is connected between the transmission output and rear axle input flange. Electrical connectors, fuel lines, coolant hoses, and air intake ducts are routed and secured. From this point forward, the truck is now considered live. It contains its engine, electrical backbone, braking systems, and operational suspension, but it's far from ready to drive. A battery module installed in steel trays along the side or rear of the frame is connected and charged. Now, the vehicle can begin low voltage diagnostics and internal system checks. The cooling module, radiator, intercooler, fan shroud, and transmission cooler is installed as a pre-assembled front-end module. This module is bolted to the front of the frame and connected to the engine via hoses and mounting brackets. Charge air ducting for turbocharged models is secured using high-pressure clamps. The HVAC condenser is integrated into this module as well, bringing together thermal management for both engine and cab. Now, with all major modules mounted and cab systems connected, the vehicle enters the fluid fill station. Here, automated filling systems inject precisely measured amounts of engine oil, coolant, transmission fluid, brake fluid, and power steering fluid. Each system is pressurized and monitored for leaks. Sensors detect flow rate, air bubbles, and fill level in real time. If any irregularity occurs, the process halts automatically, and a technician is dispatched to correct the issue before moving on. Now that the Freightliner truck has its full frame, drivetrain, cab, cooling system, fuel and air systems, and operational electrical circuits, it enters one of the most sophisticated and diagnostically intensive areas of the entire plant, the calibration and alignment zones. Here, machines begin to speak to machines, and software begins to take control. The first step is a power-on diagnostic. With the battery system now live and the truck's electrical backbone fully connected, technicians initiate the onboard computer systems. This includes the engine control module, transmission controller, ABS module, airbag control unit, body control module, and telematics gateway, among others. At this moment, the truck boots up, like powering on a small data center on wheels. A handheld or overhead diagnostic interface is connected to the vehicle's onboard diagnostic port. This interface communicates with the entire network of controllers using protocols like SAE J1939 and KN bus. The technician initiates an automated diagnostic sequence that verifies communication with all electronic modules. If any controller fails to respond or reports a fault code, the process halts, and the vehicle is flagged for further investigation in a rework bay. Otherwise, it proceeds to electronic calibration. Calibration is a critical process that sets each truck's electronics to match its unique configuration. No two trucks rolling off the line are exactly alike. One may be a day cab designed for regional haulage, while another might be a sleeper cab configured for coast-to-coast operations with collision mitigation systems and adaptive cruise control. The calibration process loads the correct firmware and parameter sets into each module, ensuring that systems like automatic transmissions shift appropriately for axle ratios, or that driver assistance systems are aware of wheelbase length and sensor positions. This is done via secure upload stations, where each truck is assigned a digital build sheet linked to its VIN. The calibration software retrieves this data from the central MES system and programs each controller accordingly. The parameters include everything from fan clutch engagement temperatures to PTO behavior and idle shutdown timers. Once complete, each module reports back its configuration status, and the entire vehicle is now digitally aligned to its physical build. Next, the vehicle moves into the alignment station. Heavy-duty laser alignment systems, mounted on rails or fixed towers, are used to measure the orientation of the front steering geometry and rear axles. Unlike passenger vehicles, trucks often have multiple axles that must be precisely aligned, not just for handling, but for fuel economy and tire wear. Toe, camber, and thrust angles are all checked in real time. Technicians use alignment racks, where the truck is driven or pushed onto a set of turntables and sensors. The wheels are clamped with reflective targets or optical sensors, and the alignment rig projects laser beams to calculate angles down to fractions of a degree. Adjustments are made on the spot, typically by rotating tie rods or adjusting shims, until all values fall within Freightliner's tight specifications. With alignment complete, attention turns to tire and wheel torque verification. Even though wheel and tire assemblies were installed earlier, every lug nut is now checked using either digital torque wrenches or wheel torque verification robots. These tools not only confirm that each nut is tightened to specification, but they record the actual torque value in the MES system, tying it permanently to that truck's build history. Any deviations are logged, and the operator must reperform the torque sequence until it passes. The vehicle now proceeds to what is perhaps one of the most dramatic stations in the entire factory, the rolling test bay. These bays simulate real-world road conditions using massive rollers embedded in the floor. The truck is driven or guided onto the rollers and secured in place using heavy chocks and hydraulic clamps. The goal is to test engine performance, transmission shifting, braking behavior, and electronic stability systems in a controlled environment. A technician enters the cab and starts the engine. Diagnostic software monitors over 1,000 real-time data points while the truck is run through a series of controlled cycles. The accelerator is gradually pressed, spinning the drive wheels up to simulated road speeds. The automatic transmission is monitored to ensure proper gear changes. The ABS is triggered under simulated braking, verifying sensor input and control module logic. While the truck is driving in place, exhaust gases are routed through a ceiling-mounted emissions probe. This system continuously analyzes the output for nitrogen oxides, carbon monoxide, hydrocarbons, and particulate matter. The truck's after-treatment system, which includes diesel oxidation catalysts, diesel particulate filters, and selective catalytic reduction modules, is monitored to confirm that emissions stay well below EPA and CARB limits. At the same time, the system also confirms that the engine software is not modified, tampered with, or otherwise non-compliant. This is done using secure electronic handshake protocols between the ECM and the test equipment. Once the rolling test is complete and all values fall within acceptable limits, the vehicle proceeds to the leak and pressure test station. This station tests all air systems for integrity, including air brakes, air suspension, and air horn systems. The truck is parked and the air tanks are fully pressurized using either the onboard compressor or an external air source. Sensors monitor the system for pressure decay, typically looking for less than a 2 psi drop over a fixed time window. If the system passes, it is deemed leak-free. If it fails, it is routed to a diagnostic bay for smoke testing or manual inspection. Similarly, the HVAC system is tested for refrigerant charge and performance. A technician activates the air conditioning and heating functions while monitoring the vent outlet temperatures. This ensures that the climate system is operating within spec before the truck is shipped. Even the windshield washer system is activated, and fluid reservoirs are topped off as needed. Now, nearing the final phase of the build, the truck enters the fit and finish inspection zone. Here, the human eye and hand still reign supreme. While automation excels at measuring torque and electrical signals, it takes trained inspectors to detect cosmetic defects, misaligned trim, or imperfect panel gaps. Workers walk around each truck with checklists in hand, inspecting everything from door seals and mirror mounts to paint finish and decal placement. The doors are opened and closed to check for proper latching. The cab lights, headlights, turn signals, brake lights, and reverse lights are all tested. The horn is honked, the wipers are activated, and the radio is briefly turned on to verify speaker operation. For trucks with sleeper cabs, technicians crawl into the bunk area and test interior lighting, power outlets, and optional features like inverters or bunk HVAC units. If the truck passes all these visual and functional checks, it's moved into the detailing area. Here, protective films applied earlier in the assembly process are removed. The cab and chassis are wiped down to remove any assembly dust or handprints. Paint is polished if necessary, and tyre shine may be applied for customer delivery presentation. As the truck sits, gleaming under overhead lights, it's finally ready for what's called a road-ready release. A final supervisor, often with years of experience, performs one last walk-around, signing off on the truck's build sheet. This triggers the MES system to mark the unit as complete, at which point a unique certificate of conformance is generated. This document certifies that the truck meets all Freightliner build standards, federal safety regulations, and emissions compliance requirements. Before any assembly begins on the factory floor, months of design and configuration have already taken place through digital modeling and client collaboration. Scania offers thousands of configurations, from cab types and engine sizes to axle arrangements and emissions profiles. Every order is configured down to the most minute specification using proprietary software systems that feed directly into the production planning systems of the factory. This digital integration ensures that each vehicle is built precisely to customer requirements, and it sets the stage for the just-in-time production model that Scania factories are known for. The process truly begins at the component level, starting with the chassis frame, the very skeleton of the truck. These frames are not formed on-site at every assembly plant. Rather, they are usually manufactured at specialized Scania facilities, such as the one in Oskarshamn, Sweden, which is renowned for its advanced laser welding and robotic bending capabilities. The raw material used is high-strength structural steel, delivered in coiled sheets or cut plates from steel mills. These sheets undergo multiple forming processes, including automated press bending, where robotic arms position the steel under immense pressure to form the longitudinal beams that serve as the base of the truck frame. After initial shaping, the steel beams enter a sophisticated robotic welding line. Here, computer-controlled robotic arms move with choreographed precision to apply dozens of welds to each frame component. Each welding head is equipped with sensors that monitor temperature, pressure, and seam alignment in real time. This ensures not only the structural integrity of the frame, but also guarantees a level of repeatability and strength that simply cannot be matched by manual welding. After welding, the frames undergo surface cleaning using shot blasting, a process that fires small steel pellets at high velocity to remove mill scale and other surface impurities, leaving behind a clean, textured finish ideal for powder coating. Next comes the anti-corrosion treatment, which is absolutely vital given the operating environments that Scania trucks face globally. The prepared frame is dipped into large immersion tanks containing anti-corrosive coatings. These coatings bond to the steel surface and offer long-term protection against rust and environmental wear. Once coated, the frame is cured in high-temperature ovens to ensure the treatment hardens properly and maintains adhesion through the vehicle's life cycle. While chassis frames are being processed, the cab structure, the cockpit of the truck, is being built in parallel. Scania's cab production is typically handled in highly automated body shops. The core of the cab begins as pressed Suzuki steel panels that are stamped into shape using massive hydraulic presses. Each press can apply hundreds of tons of force, transforming flat sheet metal into complex structural elements like roof panels, side walls, and floor pans. These pressed panels are then moved by robotic arms into positioning jigs where they are tack welded together to form the basic cab shell. The welding of the cab shell is another highly automated process. Industrial robotic arms, fitted with multiple welding torches, navigate around the jig to apply hundreds of spot welds with exacting precision. Sensors track the positioning down to millimeter level tolerances, ensuring every cab structure is perfectly square and secure. As with the chassis frame, once the cab shell is fully welded, it is subjected to shot blasting and anti-corrosion dipping. After treatment, the cab shell is baked in industrial curing ovens and then passed into the next phase, painting. The painting process is one of the most visually striking steps in the factory. Trucks are typically painted in customer-specific colors, and Scania's paint shops are designed to switch colors rapidly with minimal waste. First, the cab shell enters a cleaning station where it is rinsed, degreased, and coated with a phosphate layer to promote paint adhesion. Next, it enters the electrocoating tank, a large bath filled with a water-based paint solution that is electrically charged. The cab is submerged and an electrical current is applied, causing paint particles to bond electrochemically to the metal surface in a uniform layer. This electrocoat layer is corrosion resistant and acts as a primer for the top coat. Once cured in an oven, the cab shell enters the color booth. This area is a climate-controlled environment where automated paint robots, guided by 3D scanning systems, apply base coat and clear coat layers with astonishing accuracy. The robotic arms mimic human wrist movements, but with far more consistency and speed. Depending on the finish, additional layers like metallic flakes or special high-gloss coatings may be added. After painting, the cab passes through a final curing oven, where the coating is hardened under controlled heat conditions. While the cab and chassis are progressing through their respective lines, work begins on the engine, the heart of every Scania truck. Scania is known globally for manufacturing its own engines, and the engine assembly takes place in facilities with a near-surgical level of cleanliness. Engine blocks arrive from foundries where molten iron has been cast into precisely machined forms. These blocks are cleaned, inspected, and then sent through CNC machining lines to be drilled, bored, and honed. Critical components like cylinder bores, oil channels, and mounting faces are machined to micrometer level tolerances to ensure proper sealing and performance. The engine assembly line is a hybrid of human craftsmanship and automated precision. Components like the crankshaft, camshaft, pistons, and connecting rods are assembled using semi-automated workstations where torque-controlled tools tighten bolts to exact specifications recorded in a central database. Scania engines are known for their modularity. Many of the components can be shared across different engine variants, simplifying logistics and repair. Each engine is assembled in stages, with sensors and barcode tracking, ensuring that every step is validated before moving to the next station. Once the engine is fully assembled, it moves to the hot test cells, where it is connected to a computerized test rig and run under simulated load conditions. These test cycles verify oil pressure, emissions output, power delivery, and temperature control. The engine must pass every parameter before it is certified for installation. Failures are extremely rare due to the high degree of automation and quality control earlier in the process. By this stage in the production process, the frame, cab, and engine are all nearly complete. The next phase is the main assembly line, a linear path where all major components are brought together. This line stretches hundreds of meters through the heart of the factory and is divided into dozens of stations, each with a specific responsibility. Trucks move along the line on large powered platforms or guided vehicles, allowing workers and robots to access all sides without repositioning. The first step on the assembly line is the chassis outfitting, where the bare steel frame receives mounting brackets, fuel tanks, air tanks, electrical conduits, and brake lines. Each part is pre-assembled into kits that arrive from sub-assembly areas and are bolted on using torque-controlled tools. Workers scan every part's barcode into the digital tracking system, ensuring complete traceability from installation to delivery. As the chassis assembly progresses down the main line, the stage is set for one of the most critical moments in the truck's birth: the installation of the drivetrain. This includes the mounting of the engine, transmission, clutch assembly, and propeller shafts, all aligned and fitted with micrometer precision. The engine, having already passed its hot test, arrives at the drivetrain installation zone pre-mounted on a subframe cradle. This subframe allows the engine to be maneuvered easily and with extreme accuracy. Overhead, automated hoists fitted with dynamic positioning systems gently lower the engine into the frame rails. A laser-guided alignment system ensures that the engine mountings perfectly match the pre-fitted brackets on the chassis. At this point, technicians, supported by robotic arms that hold the engine weight, secure the mounting bolts using calibrated torque wrenches. Every bolt torque is recorded and logged digitally to create a traceable quality certificate tied to the vehicle's serial number. Following engine installation, the gearbox, a heavy and complex component, is hoisted into position behind the engine. Scania often uses its own automated manual transmissions, which integrate seamlessly with the engine via a robust clutch assembly. The clutch mechanism is pre-aligned with the flywheel, and the entire transmission unit slides onto guide pins with barely a millimeter of clearance. Here, technicians connect the hydraulic lines, gear linkages, and electrical connectors that allow for automated gear shifting, engine brake interaction, and adaptive cruise functionality. With the drivetrain in place, attention turns to the rear axle and suspension systems. Depending on the truck's intended use, long-haul, construction, or specialized applications, different axle configurations are applied. Some trucks feature a single rear axle, while others utilize tandem configurations or even additional tag axles. The axles arrive pre-assembled from Scania's axle plant, complete with brakes, hubs, and suspension linkages. They are lifted into place by hydraulic jacks and bolted to the chassis with spring packs, air bellows, or hydraulic suspension systems already integrated. Next comes propeller shaft installation, connecting the transmission to the rear axles. These shafts are balanced dynamically at the supplier's facility to prevent vibration. Universal joints are fitted with greased couplings and protective covers, ensuring long-term durability under high torque loads. At this point, the foundation of the truck's powertrain is complete. However, without electrical and pneumatic systems, the vehicle would remain lifeless. The next station handles electrical harnessing and air system integration. Scania trucks feature an extensive network of electrical harnesses, connecting everything from the engine control module and dashboard to rear light clusters and sensors. These harnesses are laid out in custom configured looms that match the specific vehicle configuration. Workers unroll and clip these looms into pre-installed brackets along the chassis rails, securing them with fasteners and protective sheathing. The plugs and connectors are then checked for correct mating, and a low voltage continuity test is performed to validate the integrity of each circuit. In parallel, technicians install air hoses and pneumatic control lines, crucial for the operation of brakes, suspension, and gear shifting systems. Scania uses color-coded hoses for easy identification: blue for service brakes, red for emergency lines, yellow for auxiliary systems. The hoses are pressure tested before installation and connected to manifold blocks fitted with quick-release couplings. Once in place, the entire pneumatic system is subjected to a leak-down test using compressed air. Pressure sensors monitor the rate of decay, and if it exceeds a predefined threshold, technicians isolate and rectify the issue before the vehicle proceeds. With the chassis now wired, plumbed, and powered, the moment arrives for the cab to be mounted. The painted and primed cab shell, now fully treated and cured, has been proceeding through a parallel line where interior components are added. Before it is even lifted onto the chassis, the cab undergoes pre-fitting of the dashboard, insulation, wiring, and climate control systems. The dashboard arrives as a single pre-wired module complete with instrument cluster, infotainment unit, control switches, and HVAC ducting. It is installed into the cab using a robotic arm that slides the assembly into its predefined slots and secures it with vibration-resistant fasteners. At this stage, seats, Pedal boxes, steering columns, and interior trim pieces are installed by skilled technicians. Each element is configured based on customer preferences, from seat fabric and placement to storage compartments and auxiliary switches. Once the interior is complete, the cab is transported via an overhead conveyor to the cab marriage station, a precise and dramatic point in the assembly process. Here, a massive cab lifting robot equipped with multi-axis movement positions the cab above the chassis. Using laser alignment sensors and pre-programmed coordinates, the system lowers the cab onto 4 chassis mounting points. Pneumatic mounts or mechanical bushings are inserted to dampen vibrations and provide ride comfort. Once seated, high-strength bolts are applied with synchronized torque tools, and the cab becomes one with the chassis. Following this, technicians connect the main wiring harness and pneumatic lines from the cab to the chassis, a process known as cab chassis interface. These connections include CAN bus data lines, power feeds, brake system controls, and auxiliary switches. As soon as these connections are complete, the vehicle is able to wake up electronically for the first time. A diagnostic tablet is plugged into the OBD port, and the truck performs a systems check. Any discrepancies or error codes are logged and addressed before the truck moves forward. The vehicle now advances to the fluid filling and commissioning station. Here, all essential fluids are added, including engine oil, coolant, transmission fluid, brake fluid, power steering fluid, AdBlue, and diesel fuel. Each fluid fill station uses metered pumps that log exact fill quantities and pressure levels. Automated sensors inside the engine and tank systems confirm that fluid levels are within range before proceeding. Once filled, the truck moves to the initial startup station, where the ignition is switched on for the first time on the line. The starter motor cranks the engine, which should come to life smoothly. A team of technicians monitors engine performance, checking for warning lights, irregular noise, or leaks. The air compressor charges the brake system, and all pneumatic circuits are tested for function. This includes pressing the brake pedal, triggering the parking brake, and cycling the air suspension. Next, the truck undergoes a dynamic rolling road test inside a fully enclosed test chamber. The vehicle is driven on rollers that simulate real-world road resistance, while various systems are tested under load. This includes acceleration tests, ABS brake tests, gear shifting patterns, cruise control behavior, emission system feedback, and traction control activation. The data is streamed in real time to diagnostic software, where engineers verify that the truck operates within all calibrated parameters. Upon passing the rolling test, the truck is driven into the final inspection bay. Here, inspectors conduct a detailed walk-around, checking for cosmetic imperfections, paint defects, missing trim pieces, or loose fittings. Each headlight, indicator, fog lamp, and brake light is checked for functionality and alignment. Mirrors are adjusted, windscreen wipers tested, and all cabin electronics, including navigation, air conditioning, radio, and USB ports are verified for operation. Once the final inspection is complete, the vehicle moves to the finishing line, where customer-specific decals, model badges, and optional accessories like bull bars, sun visors, or additional lighting rigs are added. Every Scania truck is tailored to its owner's vision, and this station gives each one its unique identity before it leaves the factory. The completed truck now rolls into the validation and delivery area, where all data from the manufacturing process, component serial numbers, torque values, diagnostic results, and inspection records are compiled into a digital certificate of compliance. This certificate accompanies the truck throughout its life, acting as a birth record for servicing and warranty purposes. At this point, the truck is technically complete, but its journey is far from over. In the next section, we will follow how Scania handles post-factory logistics, transport, dealer preparation, and delivery to the end customer. Along with insights into technological innovations, and modular production strategies that continue to shape Scania's dominance in global trucking. Once the truck passes its final on-site validation and is cleared for delivery, it enters a new phase in its life cycle: post-factory logistics and outbound handling. This transition is just as carefully orchestrated as the build itself. A Scania truck may be fully assembled, tested, and polished, but before it can reach the customer, it must navigate a labyrinth of post-production processes including staging, transport planning, documentation handling, and final handover preparation. This stage marks the convergence of manufacturing precision and supply chain excellence. The first step in this process is vehicle staging, which occurs in a designated outbound yard adjacent to the factory. This outdoor staging area is organized with military-grade precision, divided into zones based on delivery destination, vehicle type, and shipping method. Trucks are driven, not towed, from the final inspection area to the appropriate staging bay. Each vehicle is equipped with temporary wheel covers and protective wraps over vulnerable surfaces like mirrors, windshields, and chrome trim. These protective measures prevent damage during transport, especially when trucks are carried on open trailers or cargo vessels. In the outbound yard, every truck is again scanned using RFID and barcode systems, confirming its identity and correlating it with a live logistics management system. This software tracks all trucks awaiting dispatch and organizes them according to optimal shipping schedules. Depending on the final destination, a truck may be routed for domestic road delivery, loaded onto a rail car, or prepared for maritime shipment if it's headed overseas. Each route comes with its own handling protocols. For domestic deliveries within Europe, trucks are often driven under their own power by certified logistics drivers. These drivers, trained in Scania vehicle systems, are responsible not only for transportation, but for monitoring the vehicle en route. Before leaving, they perform a second-round walk-around inspection, checking fluid levels, tire pressures, and verifying that the truck matches its shipping manifest. Each journey is GPS tracked and time logged, ensuring total visibility for the customer and Scania's distribution center. If the truck is destined for international export, the logistics become more complex. Vehicles headed for distant markets like South America, Asia, or Africa are transported in batches, often using ro-ro vessels, or roll-on/roll-off ships. Prior to shipment, trucks undergo a pre-export treatment. This includes draining fuel to a minimum safe level, checking emission systems to meet port regulations, and applying additional weatherproofing layers to vulnerable components. If local regulations require specific emissions calibrations or market-specific software updates, these are applied at this stage by an outbound technician using a portable diagnostics tablet. Trucks bound for shipping are driven onto specialized transporters and secured with heavy-duty wheel chocks and tie-down systems. These transporters then carry them to port terminals, where logistics partners manage loading onto ro-ro decks using low-speed maneuvers to protect drivetrains. Throughout this entire handover process, every movement is tracked, and a digital chain of custody is maintained. In some cases, vehicles are not shipped fully assembled. For certain regions with import restrictions or high shipping costs, Scania employs a CKD strategy: complete knockdown. In this method, trucks are partially disassembled after factory completion and packed into containers, then shipped to regional assembly centers. Here, local teams reassemble the trucks under supervision, with full adherence to Scania's engineering and quality standards. This allows Scania to maintain a global footprint without needing a full manufacturing line in every country. Back in Europe, however, trucks that remain in their final configuration are delivered either to regional logistics hubs or directly to dealerships, depending on customer contracts. These logistics hubs serve as a final buffering point before customer delivery. Here, each truck is cleaned again, checked for any transport damage, and in some cases, fitted with market-specific accessories like tachographs, radio equipment, or fleet telematic systems. These are often added just before delivery to ensure compliance with local transport laws or client specifications. Once the vehicle reaches a Scania dealership or customer depot, a final pre-delivery inspection, or PDI, is conducted. This check is performed by certified dealer technicians who cross-reference the vehicle's production history with a detailed checklist covering all operational systems. This includes cabin electronics, tyre and wheel torque, headlight alignment, climate control operation, door seals and warning systems. Any required updates to onboard software, such as navigation databases or telematics modules, are downloaded and installed. At this point, the truck is nearly ready for handover to the customer, but Scania doesn't simply hand over the keys. For fleet clients or first-time buyers, a dedicated Scania delivery specialist may conduct a full walkthrough of the truck's systems. This includes explaining the adaptive cruise control functions, emergency braking systems, lane departure warnings, engine braking modes, and fuel-saving strategies. Drivers are often given a demonstration of how to use Scania's onboard telematics system, known as Scania Fleet Management, which allows fleet operators to monitor fuel consumption, driver behavior, vehicle health, and maintenance schedules in real time. This entire process, from component welding to client delivery, is only possible due to the extraordinary level of digital integration within Scania's production and logistics ecosystem. Every part, process, and movement is connected through a unified IT platform that synchronizes planning, inventory, production, and outbound delivery. This digital backbone allows Scania to offer mass customization at industrial scale, which is rare in heavy vehicle manufacturing. Beyond the sheer logistics of delivery, what truly sets Scania apart is its modular architecture, a production strategy that deserves closer inspection. Unlike many truck manufacturers that rely on rigid product lines and bespoke configurations that increase complexity, Scania uses a tightly controlled system of shared components and scalable designs. For instance, the same type of engine block can be used across multiple power ratings, with changes in turbocharging, fuel injection mapping, or transmission pairing creating different performance profiles. Cab shells also share mounting points, crash structures, and roof lines, with final variations created through bolt-on panels, interiors, and accessories. This modularity dramatically reduces the number of unique parts required on the factory floor, streamlining logistics and reducing time between customer order and vehicle build. It also ensures that spare parts are widely compatible, simplifying aftermarket servicing and reducing downtime for fleet operators. For Scania, modularity is not just a design choice. It is a strategic manufacturing philosophy that underpins everything from tooling and robotics to workforce training and dealer support. Inside the factories, this approach enables a high degree of automation. Robotic systems handle repetitive, precision-critical tasks such as welding, painting, and component fastening. Yet the human role remains central, especially in final assembly, inspection, and troubleshooting. Scania invests heavily in worker training, with programs that teach technicians how to read digital work instructions, use torque validation tools, and interpret real-time diagnostics data from vehicles in production. These skills are critical in maintaining quality across a product range that offers nearly infinite customization. To further enhance efficiency and quality, Scania has implemented smart factory technologies, including IoT sensors embedded throughout the production line. These sensors monitor equipment status, production flow, and product quality in real time. If a robotic welding arm shows signs of drift, or if a torque gun applies a value slightly out of spec, the system alerts supervisors instantly. Predictive maintenance algorithms analyze these data streams to prevent unplanned downtime, allowing equipment to be serviced before failure occurs. Sustainability is another cornerstone of Scania's manufacturing model. The company has made major investments in reducing the environmental impact of its facilities. This includes using renewable electricity, water recycling systems in paint shops, and closed-loop material recovery processes. For instance, steel offcuts from cab panel stamping are collected, sorted, and returned to suppliers for reprocessing. Paint overspray is captured and filtered before it reaches the atmosphere, while heat generated by curing ovens is recycled to warm nearby buildings. Even the logistics fleet used to move trucks from plant to port has undergone greening. Many Scania factories use their own battery electric or gas-powered truck transporters for short-range movements, reducing emissions around the factory campus. Scania's long-term goal is to create a fossil-free value chain, meaning not just fossil-free trucks, but a zero-emissions process behind every vehicle's creation. What emerges from all of this is not just a truck, but a precision-built, software-integrated, environmentally conscious transport machine designed to serve its owner with maximum uptime and minimum operating cost. Every bolt torqued, every panel painted, and every test completed is done with the understanding that this machine will soon be barreling down highways, climbing mountains, or navigating mines, often in the most demanding environments on Earth. And so, as a freshly built Scania truck pulls out of the outbound lot under its own power, fully tested, aligned, and gleaming in its custom livery, it carries with it not just cargo, but a legacy of Scandinavian engineering, lean production mastery, and digital age innovation. As the newly minted Scania truck rolls off the assembly line and onto the road, its journey as a manufactured product may be complete, but its role as a data-rich, high-performance logistics tool is just beginning. What differentiates Scania in the world of heavy-duty vehicles is not just its robust physical engineering, but also the intelligent integration of software and digital systems embedded throughout the truck. These features are not just bolted on at the end of production. They are enabled and supported throughout every stage of the manufacturing process. At the heart of this smart infrastructure is the Scania Communicator, a telematics control unit installed during the cab outfitting phase. This device connects the truck to Scania's fleet management system and remote diagnostics platforms. It functions as a two-way communications gateway between the vehicle and Scania's global network, transmitting real-time data on vehicle health, driver behavior, location, and fuel consumption. While the physical hardware is relatively compact, its installation is incredibly precise. During assembly, technicians route antennae, signal cables, and CAN bus interfaces through pre-designed channels in the cab, ensuring electromagnetic compatibility and resistance to vibration. The communicator's integration enables predictive maintenance, a significant evolution in vehicle lifecycle management. Throughout operation, the truck continuously monitors dozens of performance parameters: oil pressure, coolant temperature, brake wear, turbocharger pressure, emission levels, and more. These data points are compared against factory thresholds, and if any system approaches a condition that could cause failure, an alert is generated. This could trigger anything from a simple driver notification to a pre-scheduled service appointment at the nearest Scania workshop. It is a direct result of a factory design philosophy where the vehicle's digital nervous system is assembled and validated just as rigorously as its mechanical one. Alongside predictive maintenance, the truck's electronic control systems, also installed and configured on the assembly line, provide a high level of operational automation. Modern Scania trucks are built with dozens of ECUs, each responsible for a specific subsystem such as engine management, brake control, transmission logic, and climate systems. These units are connected via a redundant CAN network architecture, which not only increases fault tolerance, but also simplifies diagnostic procedures. During production, technicians use factory-grade diagnostic terminals to flash the appropriate firmware to each ECU, calibrate its behavior based on the truck's configuration, and verify communication across the entire electronic network. Scania's modular philosophy also extends to advanced driver assistance systems, many of which are pre-installed on the production line but activated or configured according to the customer's specifications. For example, the radar sensors used for adaptive cruise control and autonomous emergency braking are mounted on the front bumper during final assembly, precisely aligned to maintain millimeter-level accuracy over the vehicle's life. Similarly, the forward-facing camera that enables lane-keeping assistance is fitted behind the windshield during cab assembly, carefully positioned with a jig to ensure a clear, centered field of vision. Once installed, these components are connected to a centralized ADAS controller, which interprets sensor input and makes real-time driving decisions. These systems are subjected to a suite of calibration and alignment procedures before the truck leaves the factory. On the test track, radar and camera systems are validated against standard reference objects and road markers. In a controlled environment, the truck is driven through a calibration tunnel equipped with reflective targets, road signs, and lane markings designed to simulate real-world conditions. The vehicle's onboard systems must correctly interpret these stimuli, and if any discrepancies are found, technicians adjust sensor positioning or recalibrate software parameters using diagnostic interfaces. The cab interior too reflects a fusion of mechanical craftsmanship and digital design. Every detail, from the curvature of the dashboard to the responsiveness of touchscreens, is a result of ergonomic research and industrial design thinking. Scania recognizes that its drivers may spend days or even weeks living inside their cabs, and thus the manufacturing process treats the interior not just as a workplace, but as a living space. During cab outfitting, highly trained technicians assemble a range of custom options, from sleeper bunks and refrigerators to infotainment systems and integrated GPS navigation units. These elements are delivered to the line in kit form, each kit tailored to the customer's build sheet. Each cab interior is assembled under tightly controlled conditions to minimize dust, moisture, and static electricity, which could interfere with sensitive electronics. Seats are bolted to reinforced mounting points welded into the cab shell during body assembly, and each one is torque checked and height adjusted based on ergonomic templates. Touchscreen interfaces and instrument clusters are plugged into the vehicle's central network and tested via digital loopback to ensure correct display and input functionality. The HVAC system, including its filters, ducting, and thermoelectric units, is pressure tested and leak checked using nitrogen injection methods before being approved for operation. Another layer of sophistication is found in Scania's drive mode management system, also programmed during the production process. Depending on the truck's intended use, long-haul highway driving, urban logistics, construction haulage, or extreme terrain operation, the engine and transmission control units are calibrated to optimize for performance, fuel economy, or torque delivery. These calibrations are not simple throttle mappings. They include dynamic interaction between acceleration profiles, shift timing, exhaust gas recirculation rates, and even cooling fan activation thresholds. Engineers use proprietary software tools during assembly to upload the correct strategy maps into each ECU and then perform a synchronization cycle, ensuring all systems operate under a unified logic framework. In high-performance applications, such as off-road or heavy-load logistics, the truck may also be equipped with retarders, differential locks, and terrain modes. These features are controlled by modules installed under the dashboard and linked to the vehicle's main control network. Their installation involves not just physical mounting, but precise firmware configuration and sensor calibration. For instance, the differential lock actuator includes a position sensor that must be zeroed against the axle's true neutral position during installation. Once installed, These systems are tested during the dynamic run phase to ensure they engage and disengage correctly under simulated load. Meanwhile, aerodynamic elements such as roof deflectors, side skirts, and underbody fairings are installed toward the end of the main assembly line. These parts are often lightweight composite materials and are affixed using vibration-dampened fasteners and adhesive compounds designed to withstand high-speed airflow and temperature fluctuations. Their role in fuel economy is non-trivial. Even minor misalignments can increase drag, so final inspection stations are equipped with laser-guided measuring tools to verify exact positioning. Assembly teams cross-check these with 3D digital overlays displayed on large screens at the workstation. Beyond the truck itself, the factory also assembles and configures support technologies such as Scania Zone and Scania Driver Support. These tools are software-based but rely on correctly installed hardware during production. GPS modules, accelerometers, and vehicle-to-infrastructure communication units. Once activated, these systems allow operators to set geofenced zones where speed, emissions output, or engine performance is automatically regulated based on environmental or regulatory constraints. All of this logic is programmed through cloud-based platforms, but it depends entirely on the integrity of the installation work completed on the factory floor. Scania's embrace of digitalization also includes its end-of-line analytic systems, which collect every data point recorded during the truck's production. These include sensor calibrations, fluid fill quantities, software versions, torque readings, and test drive results. Once the truck completes its final quality checks, all this information is compiled into a digital build certificate, stored in Scania's central server network. This certificate not only proves the vehicle's compliance with legal standards, but it also becomes the backbone for future updates, diagnostics, and warranty assessments. Because of this meticulous build documentation, over-the-air updates can be rolled out to Scania trucks even after they have left the factory. The communicator module facilitates this functionality, allowing engineers to deploy firmware improvements, bug fixes, or performance upgrades without requiring the truck to return to a service point. This capability, made possible only because the production process embeds software management from the beginning, is rapidly becoming a key differentiator in the world of commercial transport. Perhaps most impressively, all of this technological complexity is achieved without sacrificing modularity, durability, or long-term serviceability. That's because every element, from wiring looms and ECUs to cab panels and control switches, is installed with future maintenance in mind. Harnesses are routed through accessible channels, ECUs are mounted in service boxes, and diagnostic ports are placed in standardized locations regardless of configuration. This consistency allows Scania dealers worldwide to service a wide variety of truck models with a common toolset and shared training, reducing cost and maximizing uptime for operators. The sum of all these innovations, from embedded sensors and adaptive software to modular electronics and digital infrastructure, is a Scania truck that operates not merely as a mechanical platform, but as a living, communicating system, capable of learning, adapting, and reporting throughout its operational life. This vision of the modern truck as a responsive and evolving tool is deeply rooted in the manufacturing philosophy that builds it. A philosophy where every bolt, sensor, and wire is installed with purpose, tested with rigor, and documented with precision. Behind every meticulously crafted Scania truck lies a vast, highly organized human and mechanical ecosystem, an integrated workforce structure combined with world-class lean production methodologies. These systems are designed not only to uphold the brand's legendary quality standards, but to continuously improve them, model after model, day after day. While the end product might be steel, rubber, glass, and code, the beating heart of Scania's manufacturing process is its people and the smart systems they use. Scania's factory workforce is divided into several highly specialized roles, each optimized for a specific part of the assembly line or manufacturing process. These include welders, material handlers, electronic assembly technicians, test engineers, paint technicians, quality controllers, and logistics coordinators, among others. However, what truly distinguishes the Scania workforce is not rigid job segregation, but a dynamic cross-functional approach. Many workers are trained across multiple disciplines and encouraged to rotate tasks, which fosters a deeper understanding of the entire truck building process and enables agile response when production demands shift. This flexibility is essential because Scania operates under a pull-based production system, a fundamental component of its lean manufacturing strategy. Rather than producing trucks in large batches based on forecasted demand, Scania builds each truck to order, with every unit reflecting a unique customer configuration. When a client places an order, that request propagates through Scania's production planning system, triggering a cascade of component manufacturing, subassembly preparation, and final assembly scheduling. Every workstation on the line is updated with this incoming configuration data in real time, enabling the workforce to prepare for exact variations even before the chassis reaches their station. To manage this complexity, Scania employs a cell-based manufacturing layout, particularly in cab and engine subassembly. In this model, small autonomous teams, called production cells, take full ownership of assembling specific components or systems. Each cell is responsible not just for assembly, but also for quality control, minor maintenance of their equipment, and implementing continuous improvement initiatives. Workers within these cells hold daily stand-up meetings to review performance metrics, quality issues, and improvement suggestions. These meetings are an embodiment of Scania's commitment to Kaizen, or continuous incremental improvement. This improvement philosophy is not left to chance. Scania empowers its workers with structured frameworks like the Scania Production System, a variant of the famed Toyota Production System, adapted for the unique challenges of modular truck manufacturing. SPS is built around key principles like right from me, demand-driven flow, and standardized work with flexibility. Each station has visual boards displaying production targets, current throughput, quality alerts, and safety metrics. Any worker, at any time, can pull an andon cord, a signaling mechanism that immediately halts production to address a problem or anomaly. Far from being penalized, such actions are encouraged, reinforcing a culture of quality ownership. SPS also ensures that work instructions are standardized and digitized. At every station, touchscreens provide step-by-step guidance for each unique truck configuration, including diagrams, torque settings, part numbers, and even short instructional videos. This system ensures consistency, even when different workers or shifts are involved. It also supports the introduction of new model variants or upgraded parts, as digital updates can be rolled out instantly across the entire facility. But the factory's brain doesn't stop at the workstation level. Scania's facilities are organized using advanced logistics and material replenishment systems. These include just-in-time and just-in-sequence delivery models. In the GT approach, components arrive at the assembly line exactly when needed, reducing on-site inventory and waste. JIS takes this a step further by ensuring that parts not only arrive on time, but in the exact order the assembly line requires them, matching the customer-specific build schedule. To make this possible, Scania utilizes autonomous guided vehicles and collaborative robots, also known as cobots. AGVs are programmed to navigate specific paths throughout the facility, transporting parts, kits, and tools from storage to workstations. These mobile units are equipped with obstacle detection sensors and onboard computers, allowing them to safely navigate busy factory environments and prioritize urgent deliveries. Cobots, on the other hand, work directly alongside human operators. They handle tasks like component positioning, torque application, and small part assembly. Because cobots are designed to operate safely around people, they can perform repetitive precision tasks while allowing human workers to focus on complex decision-making and quality assessments. One of the most advanced implementations of lean philosophy at Scania is its digital twin system. This virtual representation of the entire truck assembly process allows engineers and planners to simulate workflows, test layout changes, and even trial new product designs in a fully digital environment before committing changes to the physical factory floor. These simulations integrate real-world production data, making them incredibly accurate and predictive. Before a new model is introduced, it is built and validated in this digital environment, ensuring the tools, workstations, and instructions are perfectly prepared for real-world production. The importance of training and workforce development cannot be overstated in this high-performance environment. New employees go through comprehensive onboarding programs, including virtual reality training simulations, where they practice assembly techniques and safety procedures in a risk-free setting. More experienced workers have access to continuing education through Scania's in-house training academy, which covers topics such as electronics diagnostics, sustainability practices, robotics programming, and leadership development. These programs ensure that Scania's workforce remains adaptive, skilled, and deeply connected to the company's long-term goals. Scania's commitment to sustainability extends well beyond the trucks it produces. It's embedded in the very operations of its factories. Each manufacturing site is governed by a green production strategy, which includes aggressive targets for energy efficiency, waste reduction, and carbon neutrality. Solar panels line the roofs of production buildings, and in several sites, geothermal energy or district heating is used to manage interior climate control with minimal environmental impact. Water used in paint shops and testing areas is filtered and recirculated using closed-loop systems, reducing freshwater usage dramatically. Waste from steel stamping, machining, and welding operations is meticulously sorted and sent back to steel suppliers for recycling, creating a circular materials economy. Even the packaging used for inbound components is standardized and reusable. Suppliers ship parts in containers that are returned, cleaned, and reused repeatedly. Scania's internal logistics fleet, used to move materials between factory sites and distribution hubs, now includes electric trucks and vehicles powered by biofuels, reducing the carbon footprint of interfacility transport. Each of these sustainability initiatives is audited and quantified, with progress reported in annual sustainability disclosures. The factories themselves are certified to international standards such as ISO 14001 for environmental management and ISO 50001 for energy management, ensuring that improvements are not only achieved but institutionalized. These practices aren't just good for the planet, they're good for production. Energy-efficient lighting, heat recovery systems, and smart building automation lower operating costs, which ultimately contribute to Scania's competitive advantage in manufacturing. Moreover, by reducing the environmental footprint of its operations, Scania aligns itself with the increasingly stringent regulatory demands in global markets, ensuring compliance without last-minute adaptation or retrofitting. But lean and green aren't the whole story. Scania also embraces operational transparency and external collaboration. Factory tours are not uncommon, not just for public relations, but for academic, industrial, and supply chain partners. These visits are carefully choreographed but open in intent, demonstrating Scania's willingness to share best practices and invite scrutiny. Likewise, feedback from suppliers, service technicians, and even end users is fed back into the production process. If a common failure mode or service complaint emerges from the field, engineers collaborate directly with line workers to trace root causes and implement corrections, sometimes within days. This culture of bottom-up innovation is rare in large-scale manufacturing, but thrives at Scania. Workers are encouraged to submit improvement suggestions, known internally as yellow cards, through a structured feedback mechanism. These ideas can range from tool redesigns and safety enhancements to procedural changes that save time or reduce fatigue. Implemented ideas are celebrated in team meetings, and successful contributors are rewarded not just with recognition, but often with career advancement opportunities. The ultimate outcome of all this is a manufacturing operation that is resilient, adaptable, and deeply human-centric, despite the heavy use of automation and digital systems. Each truck, though shaped by machines and moved by algorithms, bears the unseen fingerprints of hundreds of skilled individuals who have each left a mark on its creation. It is a deeply collaborative process where man and machine act not in opposition, but in orchestration.